Good day. Thank you for joining us today for our recording of the BC Energy Step Code Compliance Calculator and Report Generator training. This training is for energy advisors and service organizations and others providing BC Energy Step Code compliance services. This training today will be delivered by myself, Peter Sundberg from City Green Solutions, and my colleague, Niels Anthonsen from EnerLytics Building Performance. Before we get started, we'd like to gratefully acknowledge Fortis BC in supporting this training financially. And we'd also like to make a territorial acknowledgement. We would like to acknowledge with respect the Lekwungen peoples whose traditional unceded territory we are presenting on today, and the Songhees, Esquimalt, and Wasanic peoples whose historical relationships with the land continues to this day. This training will be delivered in two parts. For part one, it'll be myself from City Green Solutions, and we'll be providing an introduction to the BC Energy Step Code. And this introduction is for very experienced EAs and those that are new to the field of the BC Energy Step Code. In the first component, we'll be talking about the purpose of the BC Energy Step Code. And then before we get into the other details, we'll focus on some of the common issues with the BC Energy Compliance Report submissions as identified by authorities having jurisdiction. Then we'll do a deep dive into the Step Code metrics, and we'll complete it with a BC Energy Step Code Compliance Manual and BC Energy Compliance Report Overview. Part two of the agenda will be delivered by Niels Anthonsen, and this will be an energy modeling demonstration and exercise where he'll review the components of the compliance calculator, show how to model a file for the percentage better than building envelope metric, provide examples and details on how to extract data from HOT 2000 and enter it into the compliance calculator. And then I'll show you examples of completing the compliance reports and have some discussions on important elements for energy advisors to take note. For part one, the key learnings that you'll come out of with this training will be having a better understanding of the purpose of the BC Energy Step Code. You'll have knowledge of the common errors and issues with compliance reports. You should know how to explain each step code metric, that is what it measures, what building components are included in each metric, the formula for calculating each metric, some information on why there are alternate options for metrics, and know the importance of the compliance manual and the compliance report. In the first section of our presentation today, we're going to talk about what is the purpose of the BC Energy Step Code. The first is that the Step Code is a performance-based approach. And that is, it's moving beyond the prescriptive requirements of the BC Building Code, where it identifies that if certain amounts of insulation are put into the attic, the floors or under the foundation, or certain windows are used, that a home can meet the requirements of the BC Building Code. Instead, there's an energy model and blower door tests. In this case, the energy advisor consults the plan evaluations and consults with the builder. They do an energy model to meet step code metrics, and they might provide an on-site mid and post blower door test. In this approach, the performance path, the energy advisor takes a range of inputs about the building. Then they do their energy model, and they come out with the outputs, which are the BC Energy Step Code metrics, as noted on the right. The BC Energy Step Code is currently a voluntary compliance option. That is, it's available for voluntary incentive programs, such as the FortisBC and BC Hydro Incentive Program. It's also available for voluntary adoption by builders at any time, at any step. And between December of 2017 and 2022, communities may voluntarily adopt the BC Energy Step Code and bylaws and policies. We'll talk a bit later about what happens in 2022 with the BC Energy Step Code. The Step Code is also in alignment with national and provincial strategies and provides a pathway to net zero ready homes. When we look at the federal policy context, we see that there's a goal that all adopt a net zero energy ready model building code by 2030. The provincial policy context is that by 2032, new buildings will be 80% more energy efficient than a home built today. The BC Energy Step Code provides a roadmap to net zero energy ready buildings. Currently, we're in the state where local governments can voluntarily adopt the Step Code and the steps that will be required within their community. But by 2022, Step 3 will become a requirement. In 2027, Step 4 will be a requirement, and by 2032, Step 5, or 80% better than building code, will become the new requirement. 2022 is not far off from where we're speaking today in December of 2020. And this is a big leap for many local governments and builders to get to Step 3. So we'll be talking about through this presentation today about what energy advisors need to do to support local governments and builders to reach Step 3. And if we're backing up 2 steps, the first step of the BC Energy Step Code is enhanced compliance. And what does this mean? It means that a Step 1 home will perform as well as or better than a building constructed to the minimum prescriptive requirements of the BC Building Code. The BC Energy Step Code has been structured, as it's called, in steps, in 5 steps. Step 1 being enhanced compliance, and Step 2 and 3 being grouped together as the lower steps. Step 4 and 5 have been classified as the upper steps. Now, we do know in many local governments have voluntarily adopted the Step Code and they've adopted Step 1. However, many builders, even brand new builders building their first home, have sometimes started with Step 5 as their first home they are building. The steps provided for the BC Energy Step Code do allow local governments to introduce it on a voluntary basis, so that builders can start with Step 1 and work their way up the step ladder, whether they want to start by going to Step 2, 3, 4, or 5. But with the acknowledgement that by 2022, Step 3 will become the requirement for the BC Building Code. The BC Energy Step Code also provides a consistent approach to advancing energy efficiency in buildings. In the past, different local governments adopted a wide range of approaches and energy labeling programs, and in many cases, industry struggled to stay on top of these different requirements. In other cases, bylaws were not always market neutral, requiring builders to build to one program or another. The BC Energy Step Code was introduced to provide a common standard for achieving building energy efficiency goals. Builders in the marketplace can still build to their preferred brand, be it Passive House, Built Green, or other, and meet the BC Energy Step Code. The BC Energy Step Code is also a series of measurable energy efficiency requirements. We'll be talking about each of these requirements in great detail today: airtightness, equipment and systems, the building enclosure metrics. And we'll be talking about the specific metric requirements as noted below. A key element of the BC Energy Step Code and a foundation for it is a focus on the performance requirements of the building envelope. And the intent of this is that so energy efficient homes are built in their structure energy efficiently, and they can use efficient heating systems, but that we should be building a structure today that's built to last. As we know, heating systems can come and go and have a life of 15 to 20 years. The building envelope is forever. The envelope first approach of the BC Energy Step Code has placed a strong focus on the house as a system concept. The house as a system concept is a building science approach that defines the house as an energy system made up of interdependent components, each of which affect the performance of each other in the entire system. By having airtightness, building envelope, and mechanical system metrics in the BC Energy Step Code, it's ensuring that builders are building homes that bring all the benefits of the house as system approach. So enhanced home comfort, affordable to operate, a healthier home, improved home equity, smaller environmental footprint, and improved home durability. The BC Energy Step Code also provides builders with flexibility to pursue innovative, creative, and cost-effective solutions. The role of an energy advisor is to support their builders to apply different strategies to meet the building performance targets. Unlike the prescriptive path where builders were limited by the prescriptive checklists and options, energy advisors can advise builders to put in more insulation in a home, to use different ventilation options and very efficient ventilation options, to really focus on the machines in the home, the heating systems, and recommend the highest efficiency heating systems. There's a focus on minimizing thermal bridges, on sealing up the building envelope with air tightness and air barriers, and to really think about the window and door options available. Unlike the prescriptive approach, the performance path has no fixed recipe, and there are dozens to hundreds of options available. And the considerations for a builder may be, what is their step code requirement? Are there any bylaws or regulations they need to meet? Do they have specific preferences on how they like to build homes? How they like to build a foundation? Are there design considerations or client considerations? This BC Energy Step Code would allow a homeowner to put more windows in the home to enjoy an ocean view, but by doing so, then they need to do other things to ensure the home meets the performance requirements of the BC Energy Step Code. In other areas, there's climate and heating degree day considerations to be met, which means builders have to build differently in those regions. And then we have new technologies and options that are coming in that allow builders to apply those and meet the energy efficiency requirements with new heating systems and so on. The BC Energy Step Code also provides a standardized reporting process for demonstrating compliance. The BC Energy Compliance Report is a translation of the BC Energy Step Code metric and technical requirements. If this report is completed accurately and completely, this is what a building inspector would need to see to approve a home for occupancy permit. The BC Energy Step Code is also a tool for consumer and industry protection. The BC Energy Compliance Report provides a verification that the home meets the minimum energy efficiency requirements of code. The compliance report also provides the potential to inform choice in the marketplace. That is, homeowners wanting to purchase a more efficient home, a step 5 home, for example, can use the compliance report to know and verify that the home they have purchased and had built for them meets that level of efficiency. The BC Energy Step Code also provides a step towards building energy literacy as operating costs are the second price tag for a home. By bringing energy efficiency and model energy efficiency into the process, we're allowing homeowners and local governments to understand how much energy and greenhouse gases are consumed and created within homes. The BC Energy Step Code is also a capacity building exercise for market transformation. By introducing it in steps and providing a wide range of supports and trainings for the industry, The BC Energy Step Code has allowed the province of BC and industry stakeholders to really take a leadership role within Canada to get our province ready for net zero energy ready buildings by 2032. So what is the BC Energy Step Code? The BC Energy Step Code is a performance-based approach. It's a voluntary compliance option until 2022 when it becomes mandatory. It's in alignment with the national and provincial strategies and a pathway to net zero. It's a first step of enhanced compliance with the BC Building Code. It's a consistent approach to advancing energy efficiency in buildings. It's a series of measurable energy efficiency requirements. It's a focus on the performance requirements of the building envelope. It's flexibility to pursue innovative and cost-effective solutions. It's a standardized reporting process for demonstrating compliance. It's a tool for consumer and industry protection. And it's capacity building for market transformation. Our next component is focusing on common issues and errors with compliance support submissions. And these common issues and errors have been identified by local governments who spoke with us in the development of this training. The first most common issue with compliance report is that while assemblies within the compliance report and the energy model are sometimes not matching the drawings or how the home has been built. And usually, but not always, this is when there's been design revisions within the process after the energy advisor has seen the plans before the home is completed. Most frequently, these are in insulation levels or in the fenestration and door to wall ratio. As identified by local governments, that demonstrates that designers, builders, and EAs are not communicating throughout the whole process about when and how changes are being made. It also identified that better procedures for communicating between the designer, builder, and EA is needed. And it also shows that there is an energy advisor responsibility to ensure that the compliance report is based on the most recent version of the plans, or more importantly, on how the home was built, if it's not built matching the plans. In the compliance report, which we'll be looking at later, there's a section that shows and says, this compliance report has been developed based on information provided by the builder and drawings prepared by this architect on this date. It's important for the energy advisor to know that they should be having the most recent version of the plans. And if there is anything within the building that does not match the plans, that they have found a way to capture this information and include it within the compliance report. Another common issue with compliance report is that there's some ERS modeling errors within the report that impacts the compliance report. So in certain cases, this is choosing the wrong building type in HOT 2000 for single family detached with secondary suite, townhome, and so on. This could be incorrectly entering standardized HRV effectiveness or incorrectly entering standardized heating efficiencies for heating systems. Or it could be as simple as how to count the second kitchen appliances and hoods and so on. Now, while ERS modeling procedures and techniques is not a focus of this specific training, we wanted to note that it's very important that energy advisors and service organizations ensure that files are modeled correctly. Another common issue is that energy advisors are not always following the submission requirements of authorities having jurisdiction. For example, Section F of the BC Energy Compliance Report is an optional section. However, local governments are allowed to require that to be submitted. And when they do require it, energy advisors do need to submit it. And in most cases, it's best practices for this component to always be completed in reports. With a few data entry points, the BC Energy Compliance Report generator will generate this section automatically for you as an energy advisor. It's also important to note that the Building Act does not prevent authorities having jurisdiction from setting their own administrative requirements to the BC Energy Compliance Report. And as long as those administrative requirements are included within a bylaw, they can do so. So it's important for each energy advisor to understand what the administrative requirements are for each local government area which they're working within. Another component was more of a general higher level component and issue. And that is, in some cases, it's been noted that energy advisors are not always understanding the step code metric outputs of the compliance report. And in this example, a building inspector asked an energy advisor, well, why a particular home wasn't passing their BC or meeting their BC Energy Step Code target. In one case, in this example, that's representative of other examples, the energy advisor said, I'm not really sure the BC Energy Compliance Report just spat out the numbers that showed did not meet this metric. For energy advisors, this knowledge of how and why a home may or may not pass the BC Energy Step Code is an essential component of their professional service providing BC Energy Step Code services. Energy advisors need to understand the how and why a home is passing or not passing on any given metric for any given step. Another not common but serious issue is when energy advisors are not following EnerGuide rating system or BC Energy Step Code compliance services rules. An example of this could be if an energy advisor submits a file to the service organization who then submits it to EnerCan without having a final blower door test or ACH data within the report. Another example could be doing a file within the EnerGuide rating system, informing the authority having jurisdiction that it was submitted to EnerCan, but not actually submitting it to the service organization or to EnerCan. Within the ERS administrative procedures, there are examples of major and minor infractions. It's important that all energy advisors are very familiar with these and ensuring that they are not doing either of these minor or major infractions. An important reminder as we enter into the rest of this training is that energy advisors hold a professional responsibility and liability. EAs need to ensure that compliance reports and energy models match the most recent versions of plans. They need to correctly model files. They need to learn and follow the submission requirements of authorities having jurisdiction. They need to complete and submit files as soon as possible. They need to fully understand the BC Energy Step Code metrics. They need to ensure that nothing is done to break the rules of the EnerGuide rating system or BC Energy Step Code compliance, whether intentionally or unintentionally. In the next component of this report, we're going to look at what the BC Energy Step Code measures. And first, it measures the performance requirements for the building envelope. Secondly, it measures the performance requirements for equipment and systems. And thirdly, it measures the performance requirements as related to air tightness. As previously noted, the BC Energy Step Code brings the building science concept of house as a system into practice. The air tightness targets, equipment and systems targets, and the building enclosure targets all ensure that the builder is building a home that brings the benefits of energy efficiency to the people that will live in that home. An important concept within the BC Energy Step Code is the concept of energy intensity, which is defined as a normalized performance metric calculated by dividing the rated annual energy consumption by the heated floor area. On the bottom of the screen, it shows the formula. In the example we have here, we have an EnerGuide rating system home of 81 gigajoules a year with 654.3 meters square. It shows that there's a rated energy intensity of 0.12 gigajoules meters squared a year. If we're looking at this at kilowatt hours a year as used in the BC Energy Step Code, we have 34.39 kilowatt hours meters squared a year. Many of the metrics within the BC Energy Step Code are intensity metrics. This is an important consideration for energy advisors to understand. This example of energy intensity is useful to compare the annual energy use of homes of different sizes on a per square meter basis. In this case, we have a medium home and a large home, both with an EnerGuide rating of 81 gigajoules a year, but with very different heated floor areas And what this example shows us is that the larger home is more energy efficient on an energy intensity basis than the medium home, even though they use the exact same amount of energy on a yearly basis. Now, for this larger home to have 34.39 gigajoules a year versus 68.81 gigajoules a year, it had to be built more efficiently. In the next section of this report, we're going to focus on the BC Energy Step Code metrics and take a deep dive into each of them. So how does the BC Energy Step Code measure? It measures air tightness in terms of air changes per hour. It measures equipment and systems in terms of mechanical energy use intensity and percentage lower than reference house. It measures building enclosures by thermal energy demand intensity, adjusted thermal energy demand intensity, or percentage better envelope than reference house. And with each one of these targets, there are different metric requirements for each step. Throughout this section, we're going to be explaining the metrics with an example training file. And that training file is a single-family detached home with a suite in climate zone 4, with 324.69 floor area of conditioned space. It has air conditioning, and it's in a local government area where they have a step code 3 requirement. Why we're focusing on a step code 3 requirement is this will be the requirement in 2022. So it provides us with an example of a home that may need to be built to this level within a short number of years. First, we'll focus on the air changes per hour metric. For a step 3 home, it needs to have 2.5 air changes per hour or less if they're going to meet step 3. Air tightness is defined and measures how much air leaks in or out of a building enclosure. And it's done by looking at the airflow at 50 pascals or other test measure divided by the building volume. When we're looking at units of air tightness measurement, there are 3 main ways of doing it. That's air changes per hour, which tells us the number of times the total volume of air in the building will be replaced with outdoor air in an hour. And this is the number we put in the BC Energy Compliance Report. There's also the equivalent leakage area, and this tells us how big are all the holes when added together. And this is a very useful way of visualizing how much air leakage there would be in a home. And then there's the normalized leakage area. And this is the ratio of the equivalent leakage area to the exposed surface area of the building. And this is a very useful metric for comparing the sort of equivalent air leakage in different sizes of homes. So in this example we have below, we have a larger home, over 7,000 square feet, tested at mid-construction, and it has a 1.06 air changes per hour, which sounds quite good in terms of air leakage. Then if we look at the equivalent leakage area, again, how big are all the holes when added together? And it shows us that it's 161 inches squared. And if you're to visualize 161 inches squared, that's quite a big area. So it's interesting to note, even a home that has 1.06 air changes per hour can actually have quite a bit of air leakage over a larger sized home. Then we have a normalized leakage area, and it shows this comparatively how much is leaking by inch squared over 100 feet squared. Like, so again, if you want to compare how well homes are doing in terms of air leakage by area, this provides us with a very useful metric and way of doing so. For energy advisors, these 3 units of air tightness measurement are very useful when you're talking about air leakage and explaining to builders or building inspectors. So why do we need air tightness testing? Well, for one, the step code has made it a performance requirement. And the second is that air tightness of a home impacts the builder's ability to achieve all the other step code metrics. So it impacts the percentage less than reference house, mechanical energy use intensity, the thermal energy demand intensity, the adjusted thermal energy demand intensity, and the percentage better envelope than reference house. Also important to note, and why we have to put so much focus as generally as an industry and for energy advisors on air tightness. Here we have some data of median air tightness results from 2017. And what it shows us as the median air tightness would not pass step 2 or onward. And we will have a step 3 requirement in 2022. And if we're not getting better than the median results of 2017, many builders would not be able to achieve the step 3 requirement, nor the step 2 requirement today. It's also important to note that this data we have on median air tightness is drawn from those builders that are already working with an energy advisor, typically building more efficient homes than the average home built in BC. So it shows that on average, all builders within the province needs to do a lot more to be able to hit the air tightness targets of the BC Energy Step Code. Now, if we're looking at the building components section of the BC Energy Step Code, that's section B, the specific area that focuses on air tightness is the air barrier system and location, in this case, 6 mil poly. However, how a home is built and all the components within it also impact air tightness. A heating system that's added in and holes drilled through the wall, if there's any penetrations through the wall, this could impact air tightness, as could the way doors and windows are installed, the way insulation and framing is happening. All of these things within a home can impact air tightness. When you're looking at section D, the BC Energy Compliance Report, we see here where it shows each of the metrics. The requirement for a step 3 home is it needs to be no more than 2.5 air changes. In this particular example, in the proposed home, it showed that the builder was going to reach 2.5. But given this is right on the target, in this particular case, an energy advisor should be advising the builder that a mid-construction blower door test is a very wise decision to make so that any improvements in the building envelope and the air tightness for the home can be done at mid-construction and prior to final construction. So next, let's look at the percentage lower than ERS Reference House. In the BC Energy Step Code metrics chart, it shows us that at step 1, the percentage better than reference house has to be 0. It at least has to meet the ERS reference house. For step 3, it has to be 20% better. In this particular case, as an envelope and systems metric, the builder has the option of either meeting or beating percentage lower than reference house or the MEUI metric. So let's look at the difference between the ERS reference house as used in the EnerGuide rating system as opposed to the percentage less than the ERS reference house used in the BC Energy Step Code. The reference rating on the EnerGuide label, as you might see here at 175, shows the ERS typical new house. And that's a home as if built to the National Building Code requirements. And it's a customized comparison of each rated home, more or less energy usage than a typical new home of the same size, location, and design. And in this rating, it includes the base loads for the home, which in the EnerGuide rating system is 25.6 gigajoules a year. So that 25.6 gigajoules per year is integrated into that 175 gigajoules reference rating number. In the BC Energy Step Code, the percentage lower than the ERS reference house includes all the same components as the EnerGuide rating system reference house, but it does not include base loads or renewable energy. When we're looking at section B of the BC Energy Compliance Report, all of the components, all of the building characteristic components are included in the percentage less than reference house. So in this particular case, a builder, an energy advisor advising that builder has many options to advise them on how to meet this metric. For step 3, the builder would need to make at least 20% better. In this particular example, we show the shows of the home has 56.4% better. So far, we're surpassing what would be the step 4 requirement of 40% better. So in this particular case, it shows that the builder is going to have no problem with passing on that metric. Now let's look at mechanical energy use intensity, or MEUI. The MEUI is an equipment and system metric, and for step 3, needs to meet 50 kilowatt hours meters squared a year as the target. However, with MEUI, there are both size and cooling system adjustments. So if we're looking at step 3 for a smaller home, rather than just 50, based on the size of the home, there's different metric targets. There's also different metric targets if it's designed with a design and construction with a cooling system. If it's a larger home with a cooling system, it would be 55. If it didn't have a cooling system, it would be 50, and so on. We'll explain a little bit more about these size and cooling system adjustments in just a moment. So mechanical energy use intensity is defined as the mechanical energy used over a year. It's normalized by square meter of heated floor area and expressed in kilowatt hours. Meters squared a year. It does not include base loads. And if you're looking at the formula, and this formula and all the formulas are integrated into the BC Energy Compliance Report, but it's useful for energy advisors to really pay attention and understand what the formula is for each of the metrics. This allows them to understand how the metrics are calculated and how to explain it to builders and others. So again, total energy consumption, kilowatt hours a year, minus base loads divided by heated floor area. So what's included in MEUI? It's energy used for space heating, space cooling, fans, service and water heating, pumps, and auxiliary HVAC equipment. In other words, less mechanical equipment or more efficient mechanical equipment allows for a smaller MEUI. When you're looking at BC Energy Compliance Report, Section B, the elements of MEUI are these ones here. Space heat conditioning, heating and cooling, service water heating, and ventilation. So if a builder was not passing on its MEUI target, you would need to recommend a more efficient system for one of these components. And again, the builder for these components has two options to pass. In this particular case, it's passing on both. The requirement is 55 maximum. They achieve that by having 22. If the builder was not to pass on the MEUI, they would still have the option of being able to pass on the underguide rating system lower than reference house metric. So let's look again at the size and cooling system adjustments and why these are in place. Why are the size adjustments there? And why it is that as an intensity metric, MEUI is disproportionately difficult for small homes to achieve because of two things. The total energy consumption from hot water within a home as modeled is the same regardless of house size. That means the energy intensity of the hot water load is much greater for smaller homes. And because MEUI is an intensity metric based on the heated floor area of the home, the larger house with the more heated floor area, it's much easier to get a smaller MEUI. Now let's look at an example of that. Here we have 4 different homes. We have a smaller home with a smaller energy consumption that easily passes the metric. Then we have a small house, a medium house, and a larger house that all have the same gigajoule and kilowatt hour energy consumption a year. These homes each have different heated floor areas. Because MEUI is an intensity metric, because we take this 58 gigajoules a year, or we take this 16,111 kilowatt hours a year, minusing the base loads, and we divide it by the larger floor area, it's easier for the larger house to have a smaller MEUI. This is a result of taking an energy consumption number and dividing it by a larger floor area, which by default is going to allow for a smaller MEUI result. However, this isn't just necessarily a free pass, because this larger home would have needed to be built more efficiently to use the same amount of energy annually than the small home. However, it does make it more challenging for smaller homes to pass the MEUI metric. And for this reason, there's MEUI size adjustments. So it allows that smaller home, which has also been built efficiently, but has a smaller heated floor area, to be able to pass the MEUI metric. So again, we see the MEUI metric here. If it would have been step 3 in a smaller sized home, it would have an allowance of 120. The larger home, as in our example, they only have to meet 50. Now let's look at the cooling system adjustment. The cooling system adjustment only applies for homes that have more than 50% of their conditioned area with cooling. And it only applies when the cooling energy is included in the actual energy consumption of the energy model. Here we have a snapshot of the design space and cooling loads from HOT 2000. It's important to note that this design cooling load is included within HOT 2000, whether or not there is actually a cooling system installed within the home. HOT 2000 provides this number so that the energy advisors and others understand what the design cooling load would be. But just because there is the design cooling load in the home doesn't mean the builder is installing a cooling system. So the cooling adjustment within the MEUI metric cannot be applied unless there actually is a cooling system within the home. So how do we determine what and whether there's 50% of the conditioned area of this home is serviced by cooling? In this particular example, it demonstrates this. We have a home floor plan with 2 mini split units, one in the master bedroom, one in the living room. If one was to just make a guess whether or not 50% of this room was going to be cooled by these 2 units, it could be fairly subjective to say whether it would be or not. For this reason, and to avoid that subjectivity in making a call about 50% of conditioned area serviced by cooling, there's a formula that functions as a proxy to determine the cooling capacity of the space cooling systems. The formula is cooling capacity of space cooling systems in watts divided by design cooling load times 100. This formula is built within the BC Energy Compliance Report, so you don't need to do it yourself. You just need to insert the data requested within the compliance report. So let's look at the building envelope metrics of TEDI, adjusted TEDI, percentage better envelope than reference house. First, with thermal energy demand intensity. Again, because it's a building enclosure metric, there's 3 different options that a builder or an energy advisor can advise the builder to select. For step 3, the target is 30. TEDI is defined as the heating energy required for space conditioning, conditioning of ventilation air, normalized per square meter of area of conditioned space, and expressed in kilowatt hours meters squared a year. Again, the formula for this, integrated into the BC Energy Compliance Report, is listed here. The TEDI includes the heat loss through the exterior envelope, air leakage through the air barrier, solar heat gain, internal heat gains from occupants, heat recovery from exhaust ventilation, internal gains from water and space heating equipment and fans. In other words, TEDI asks and tells us how much heat is needed to replace heat loss. And the more efficient the building envelope within the home, the lower the TEDI. When we're looking at section B of the BC Energy Compliance Report, these are the sections that are included within the TEDI: ventilation and these building envelope components. And if we look at section D of the BC Energy Compliance Report for the TEDI, it shows us that 30 is the requirement, and this home meets and beats that requirement by achieving 25. Now let's look at adjusted thermal energy demand intensity. What's included within the metric and why it was introduced. This is a metric, but there's a much more complicated way of determining how you pass that metric, and we'll explain this in a moment. So adjusted TEDI is defined as exactly the same thing as TEDI. It includes space conditioning, conditioning of ventilation air, normalized by square meter of area of conditioned space, expressed in kilowatt hours, but there's adjustments based on the heating degree days of the particular location where this home is being built. Adjusted in TEDI includes the same components as TEDI: heat loss through the exterior envelope, air leakage through the air barrier, solar heat gain, internal gains from occupants, heat recovery from exhaust ventilation, internal gains from water and space heating equipment and fans. So it's exactly the same in terms of how it's defined and what it includes as the TEDI. And again, in section B of the BC Energy Compliance Report, it includes the same building characteristic elements. So why do we have adjusted TEDI? And what analysis of various BC Energy Step Code reports tells us is that TEDI is disproportionately difficult to achieve for homes in locations with more heating degree days than others within the same climate zone. And what adjusted TEDI does is allow builders in colder parts of a climate zone to adjust the requirements of the metrics they need to meet based on the heating degree days of the location, rather than using a single requirement for the entire climate zone. So here we have an example, climate zone 5. We have both Prince Rupert, which is much further north, and Nanaimo. In this particular scenario, in Nanaimo, we have 3,000 heating degree days. We have Prince Rupert with 3,900 heating degree days. And in both cases, there's the standard TEDI requirement of 40. Obviously, with more heating degree days in Prince Rupert, it's much more challenging to pass a TEDI than it would be in Nanaimo. And for this reason, the BC Energy Step Code has created a sliding scale of metric targets for each step that would show us based on the degree days rather than just the climate zone. So in this particular scenario, it allows us to go in for Nanaimo. We have an adjusted TEDI requirement of 40. For Prince Rupert, we have adjusted TEDI requirement of 49. When energy modeling, energy advisors should always use the appropriate heating degree day data. To access this information, energy advisors should consult with the authority having jurisdiction. And if you're unable to access it from this source, you should look to Division B of Appendix C of the BC 2018, as identified on the chart on the screen. Remember, as we previously discussed, to find the heating degree data, you should consult directly with the authority having jurisdiction first to identify if there's any localized heating degree day data you should use, or if you cannot find it from this source, go to Division B, Appendix C of the BC 2018. So let's look at percentage better envelope than reference house. This is a new metric that was more recently introduced, and it's one of the additional building enclosure metrics included within the BC Energy Step Code. So again, a builder has the option of meeting the TEDI, the adjusted TEDI, the percentage better envelope than reference house. In this particular scenario, for the Step 3 example, the builder needs to meet 10% better envelope than reference house. So what is this? How is it defined? It includes the heating energy required for space conditioning, conditioning of ventilation air, and it's expressed in the percentage difference between the auxiliary energy required of a modified proposed house to the auxiliary energy required of an ERF reference house. It includes heat loss through the exterior envelope, includes air leakage through the air barrier, solar heat gain, internal gains from occupants, and importantly, it neutralizes the heat gains from domestic hot water and space heating equipment and ventilation fans by modeling the same in the proposed in the reference house. Also important to note, it does not include heat recovery from exhaust ventilation. The building characteristic summary of the BC Energy Compliance Report for this metric, it includes all of these elements. Again, all of the building envelope elements. So why is there a percentage better envelope than reference house option? Well, because TEDI is based on auxiliary energy, which is the amount of additional energy needed to heat a home once internal gains and passive solar gains are taken into account, it can be very challenging for some homes to pass the TEDI. Here we have an exaggerated example of a home like we built in a large farm area, has been built with trees surrounding it. In this particular case, there's very little passive solar gains. And in this particular scenario, it may be challenging for that home to meet the TEDI metric. The second issue is that because TEDI is based on the heated floor area of the home and not the volume, it can be more challenging for some homes to be able to meet. So for example, this image here, we have an image of part of a home with some more complex features, in this case, a cathedral ceiling, and it can make it harder for this home to meet the TEDI requirements. Because in this case, this complex feature of the cathedral ceiling adds building envelope surface area and volume, which increases space heating demand, but because TEDI is based on floor area, it can have a harder time meeting the MEUI metric. So again, TEDI is space heating demand, kilowatt hours a year, divided by heated floor area. But if we have a building with a lot of extra volume, increasing space heating demand, it can be more challenging to meet this intensity metric of the TEDI. So the solution to these two challenges was the introduction of the percentage better envelope than reference house, which compares the percentage difference between the auxiliary energy required of a modified proposed house to the auxiliary energy required of an ERS reference house. And in part 2 of this presentation, my colleague Niels will be doing some detailed explanation of how this modeling exercise is undertaken. So why and how do you modify a proposed house? Why is to create a more pure envelope metric. How do you do it? You model the hot water, space heating, and the ventilation system so they exactly match the ERS rule set for the reference house with no heat recovery from ventilation air. So we have a scenario where there's a reference house, the proposed house where the mechanical equipment and efficiencies are identical. In this case, it neutralizes the heat gains from water and space heating equipment and ventilation fans. Again, as noted, my colleague Niels will be showing this in detail and explaining it in part 2 of this presentation. So what the percentage better envelope than option does provides an alternate way to demonstrate whether or not sufficient envelope performance improvements have been made. The difference in auxiliary energy is now completely due to the improved building envelope of the proposed house. It ensures fairness across a greater range of building designs, and it's based on a similar approach being considered for the Model National Building Code. In the next section of this presentation, we're going to focus on the BC Energy Step Code Compliance Report User Manual. The BC Energy Step Code Instruction Manual for BC Energy Step Code Compliance Reports is found on the BC Energy Step Code website, and it provides you with detailed instructions on how to complete the BC Energy Compliance Report. It's also important to note that each time there's a change in the BC Energy Step Code or an enhancement in the instructions on how to generate a BC Energy Compliance Report, these will be included in the compliance manual. It also shows us different versions of the report and which version of the BC Energy Compliance Report should be used based on the date when the building permit application was submitted. So it's very important that you use the correct version of the BC Energy Compliance Report and that you refer to the manual regularly to identify where there's been changes made in the processes and instructions for doing BC Energy Compliance reporting. There's some very important notes. Legacy versions of Excel may not be supported. So if you have an older computer you're using with older software, be sure to upgrade it, as not all the functions of the compliance report generator may be supported for older software versions. You should always set your HOT 2000 file to metric units to ensure that you're pulling the right data and inserting within the reports. It's also important to note that AHJs may require evidence that any changes to the building design after the building permit, but before completion of the BC Energy Step Code, is the data that must be included in the BC Energy Compliance Report. Another important element is that you need to keep the P-file section of the calculator static when updating the N-file report to keep a record of what has been submitted. And that it's important to follow rounding calculation instructions. Now, many of these rounding calculation instructions have been integrated into the BC Energy Compliance Calculator, but if you're doing any manual calculations or other calculations and are not you doing it through HOT 2000, there are specific rounding calculation instructions for the BC Energy Step Code. The Compliance Report Manual provides detailed line-by-line instructions for each section an element of the BC Energy Compliance Report. So it lets you know what you should be filling in and which data will be manually entered in one report and which will be auto-populated in different reports. So for example, it'll tell you what building type and provides definitions. It tells you where you should be getting your heating degree day information. Floor area of conditioned space is a new section that's been added into the compliance report in later versions, as it's very useful for validating metrics and for local governments to see this number to understand why the metrics are different on reports for larger homes versus smaller homes, for example. In there's checkboxes, so depending on which path you're doing, it tells you which sections of the report you should be completing, whether you're doing 9.36.6 or 9.36.5 and so on. In the report, for example, again, as we spoke about earlier, about heating degree days, it tells you where you should be finding the information for heating degree days. So in all cases, when energy advisor are being asked to reference external documents to fill this out, the BC Energy Compliance Manual tells you where to go to find that information. It also explains where you should be finding that information in HOT 2000. For example, on the effective RSI value and efficiency, it tells you where within HOT 2000 you should be finding this information. In this particular case, it's the HOT 2000 tab separated values, TSV file, and it tells you where to look for this information. Also importantly, it tells us some very specific guidelines. For example, the RSI information, you're supposed to be using the weighted average effective RSI value. And it also tells us where we should be finding this information. While there may be differences between what architects use and energy advisors do, architects will use code generalized assumptions for RSI values, whereas HOT 2000 uses specifics, the geometry of the building, accounting for framing, approaches, corners, and so on. Energy advisors are supposed to pull this RSI value from HOT 2000, not from the building plans. This is also important to note for building inspectors if they wonder why you've used different RSI values than what's been included in the plans. It's because the instructions for the BC Energy Compliance Report says to pull it from HOT 2000 because they will be more accurate than what would be included on the plans. Conversely, for windows, you should be using the information available in architectural drawings. And that's because the data within HOT 2000, fenestration door wall ratio is in HOT 3000, includes skylights, which should not be included. So again, when filling out section B, the FDWR component of section B, this should be pulled from the architectural plans, not HOT 2000. The compliance report also has a section C for 9.36.5 energy performance compliance. When doing this, energy advisors should use the NRCan instruction document titled here, Guidelines for Using HOT 2000, version 11 to demonstrate compliance with subsection 9.36.5. Further guidelines for energy advisors and entity monitors on using this approach are pending and will be provided at a later date. It's also very important for energy advisors and others using the BC Energy Compliance Report to put the correct checkbox in how and which approach, which calculation areas they're using to generate this report. So in most cases, people are using the EnerGuide rating system. They should be clicking on that. If you're using subsection 9.36.5, you should check on this box. If you are using the instructions, which we'll introduce in a moment, for modeling attached ground-oriented Part 9 buildings, then you would check this approach, as that's an alternate approach to meeting the BC Energy Step Code. Section D of the report is the key area of the report. This is the summary that allows the building inspector and the builders to know how they have passed BC Energy Step Code for each metric, or conversely, if they did not pass on any one of the metrics, it would identify this here. The BC Energy Compliance Report Manual also outlines what should be included in the basic information section. In this particular section, if you're an EnerGuide rating system energy advisor, and only if the file was submitted to the service organization and then submitted to NRCan, should there be an EnerGuide P file number listed here. If this file was done in HOT 2000 and not submitted to the service organization, then that information should not be included there. There's also an important reminder in this section to don't check it unless you do so. Enter this code into infill field 8 of HOT 2000, and that allows stakeholders in British Columbia to know that that HOT 2000 file is a BC Energy Step Code file, and whether the utilities, province, or others request that information, they can request all of the files that have been done for the BC Energy Step Code in British Columbia and get that data from Natural Resources Canada. Section F, again, as in the BC Energy Compliance Report, is an optional section. And so this is optional in that these are not requirements of the BC Energy Step Code, but these are information metrics that have been requested by stakeholders, be they utilities or local governments. They are automatically generated through the BC Energy Compliance Report and Calculator, but the energy advisor does need to take an extra step to make sure they're filled out. If they are required by the local government, you must provide this section of the report to them. And generally it's a best practice, given that it's almost automatically generated, to include it with all BC Energy Compliance reports. Section G of the BC Energy Compliance Report allows the energy advisor to identify if the builder they're working with is planning on building to a certain energy labeling program, be it Built Green, Passive House, the CHBA Net Zero program, or other program. Also included in the BC Energy Compliance Report User Manual is all kinds of details on how to manually calculate the metrics and where within HOT 2000 you can identify the data that you need to put within the BC Energy Compliance Report. So this information is in the Excel calculator as well in one of the tabs, which Niels will introduce, but it's also in the compliance manual along with sample calculations. And these are there to help energy advisors understand how the calculator works and how the metrics are calculated. So again, if you're new to the BC Energy Step Code or interested in how the BC Energy Compliance Report generates that metrics, there's definitions of the formulas and examples of how it's calculated. So this will be gone into more detail by my colleague Niels in part 2 of the presentation, but we're also going to do a brief explanation of the ground-orientated attached for Part 9 buildings instructions. So within the compliance report manual, there's some very detailed instructions on how to model attached ground-orientated Part 9 buildings. So these types of buildings fall into 2 different categories as per the undergrad rating system. They're non-MURBs and MURBs. And non-MURBs are those ground-oriented Part 9 buildings that have with 2 or more units where no units have any vertical overlap. So that would be row homes, quadplexes, semi-detached. So imagine if this was a 3-plex. There's no vertical overlap, 1-story 3-plex, no vertical interlap. We would call this a non-MURB. The MURBs are those buildings, let's just say this was a 2-story with 6 units where there would be some vertical overlap between. So we can see one building is vertically overlapping another building here. This would be a MURB. In the BC Energy Step Code, we only have instructions available for those non-MURB attached ground-orientated Part 9 residential buildings. So this example with no vertical overlap, you can use the BC Energy Compliance Report and the alternate instructions for this type of building or a 6-plex that has no vertical overlap. The context within the BC Energy Step Code for the ground-orientated attached buildings instructions is that the BC Energy Step Code requires whole building energy modeling and blower door testing. And there's no code requirement for an air barrier between attached units. So requiring each unit to achieve an air tightness requirement, as the BC Energy Step Code does for this building type, would require a code change. The challenges we've come across in BC is that MURB attached ground-orientated buildings only have instructions for modeling and testing as individual units by the undergrad rating system. It can be very challenging to cost-effectively provide a whole building blower door test. And for builders, it can be challenging to hit air tightness requirements when there's air leakage between the party walls and with current common designs and construction practices sort of resulting in more air leakage between party walls of non-MURB units. So what the BC Energy Step Code has done is develop an alternate procedure for these types of buildings. That alternate procedure consists of the following 4 steps. An undergrad rating system energy model and blower door test is conducted for each unit. The data from the energy model is inputted into the attached non-MURB calculator in the BC Energy Step Code compliance report generator. And then there's a permission to apply a 0.5 ACH adjustment for each attached ground unit where the air tightness testings values are 2.0 air changes or greater. So for example, if a home or a unit within the building has 2 air changes per hour, then you can input 2.0 minus 0.5 to get a 1.5 air change per hour result. For those results between 2.0 air changes per hour and 1.50, you can reduce that to 1.50 air changes per hour. Anything below a tested result of 1.5 air changes per hour must then use the value as tested. Then the calculator sums and where appropriate averages the metrics for each unit to achieve the step code metrics for the building as a whole. This sounds kind of complex, so we have an example of a row house air tightness test for 4 units. In this particular example, each unit had a different air change per hour result as tested, which is shown here. And each of them have a different exposed surface area, as shown here. What you do within this particular case is you take your as tested result and you minus 0.5. So in here, be 0.37 ACH, you minus 0.5 for 3.2. To get the whole building, one air tightness result for the whole building, you take the exposed surface area, you times it by your adjusted ACH for that unit, you add it to the same results for the next building, and so on for each building, and then you divide it by the total exposed surface area of the building. And what this allows is the exterior surface area weighted average of all the units adjusted air tightness results. And this allows us to come up with an air tightness result for the full building rather than a unit. That's a weighted average air tightness testing result. All of these calculations in the formula have been built into the BC Energy Compliance Report, so you just need to enter the as tested data and the calculator will do the rest of the results for you. A similar type of formula is done for determining a TEDI for a non-MURB ground-orientated attached building. What it takes is the auxiliary energy divided by the total heated floor area. In this particular case, is you add up all of the auxiliary energy required, you add up all of the total heated floor area and you divide it, times it by 2.77.78, you would get a building weighted average TEDI result. In the final section of this training, we'll do a review of the resources that are available for energy advisors and other stakeholders. First and most important resource for you to be familiar with is the energystepcode.ca website, where there's a range of resources and information available for all stakeholders, including and most importantly for energy advisors, the compliance tools for Part 9 buildings and the compliance instruction manual. It's important to note that for the compliance manual and the compliance calculator, it's important to check back semi-regularly to ensure that you have the latest version. Both the manual and the compliance report are updated periodically with enhancements and new instructions on how to better and more accurately model for the BC Energy Step Code. There's also a range of very useful bulletins that provide additional details on all kinds of important technical issues. All energy advisors should have read and understood these and likely have downloaded them and be at the ready for reference as needed. There's also a range of handbooks and guides and resources that are available for different stakeholders. In many of the cases, while for particularly those that are new to the BC Energy Step Code, these may be essential readings, but they're also useful to recommend to stakeholders that you may interact with, whether they be building officials, builders, or others, so that you can recommend that they read those manuals if it appears they need that information. The Builder's Guide provides a wide range of good resources, building science information, and a good overview of the BC Energy Step Code. The Illustrated Guide to Achieving Airtight Buildings is an excellent resource that provides a lot of details about air barrier approaches. If you're not already registered for the BC Energy Step Code newsletter, this is an important communication piece used by the province and stakeholders to deliver information about new trainings, changes to the BC Energy Step Code, and other updates. For energy advisors, if there is going to be new BC Energy compliance reports released, it is likely going to get announced in this stakeholder update. So it's worth the time registering at this link and reviewing in detail each newsletter as they are released. Another important resource for energy advisors is the betterhomesbc.ca website, which provides a wide range of resources on rebates and other information for new construction, as well as information on rebates for existing home retrofits. Importantly, for all energy advisors is that there's a search tool that allows builders and other stakeholders to identify energy advisors. So that allows any stakeholder to go on and say if they're constructing or retrofitting a home, and where is the home located, then it allows them to identify all the energy advisors, which in this case would be servicing Richmond. Also, very importantly for your builder clients and for you to be aware of so you can inform your builder clients, there's a rebate search tool. And as all energy advisors know, rebate programs change over time. There's new introductions. Sometimes there's increased funds that are available, and you want to be aware of what rebates are available so you can advise your builders. On the rebate search tool, it allows you to identify if you're building or retrofitting a home, where the home's located. Then you can search by heating type or for all heating types, as this example does, and it provides you with an updated list of all of the rebates that are available. By clicking onto any one of these, it will provide you with the details about the funds that are available for your builder clients. Importantly, there may also be rebates and or subsidies for energy advisors. For in this particular case, there's subsidies for free mid-construction blower door test. If you're an energy advisor, that is a subsidy for your service, so you want to be aware that it is available. In this particular case, we're looking at Richmond. And there's other important rebate information or program information that is useful for you to bring to your builders, such as mortgage refunds and tax refunds and so on.
Hello, my name is Niels Anthonsen. I'm with EnerLytics Building Performance, and I'm an EA and also an energy modeler for Part 3 buildings, and I do a fair amount of prescriptive consulting as well on the energy codes and energy standards. This morning, I'm going to take you through a couple of hours of, I'm just getting this, and we've got a screen share here. I'm going to run you through the BC step code compliance workbook in some detail. So first, we're going to do an overview of the tabs. Then we're going to model a HOT 2000 file for the percent building envelope better than reference house metric. And then we're going to extract data from HOT 2000 and enter it into the calculators. And then we're going to show how to fill out some of the compliance reports. So first of all, starting with the tab overview, this takes about 30 minutes. And then you can see the times here. And all of this takes about 2 hours for us to get through. And I'll be breaking it up into its A, B, C, and D pieces that you see here. So starting with the tab overview, in the BCBC Step Code Compliance Workbook that we have here for Part 9 modeling for HOT 2000, this is not for Part 3. I believe Susan from Focal Energy gave you a part. There's a webinar out there for Part 3. This is for Part 9 residential. This is the workbook. The only difference between this workbook and the workbook that you would be having is you will notice along the bottom here these tabs, and you can see them all along the bottom here. And the only difference between what I have and you have is that I've got an agenda tab on the left, and I have some other tabs hidden that I'll be using later in this webinar. And there's basically 8 tabs along the bottom. And there are 4 supporting role tabs, 2 calculator tabs, and 2 compliance report tabs. So working from bottom to top here, the compliance report tabs are the first 2 tabs that you'll see in the workbook. The calculator tabs are these 2 tabs, the single family home and MERB calculator and the attached non-MERB calculator. So attached non-MERBs meaning basically townhomes or duplexes. They're attached side by side. There is no vertical overlap on them, because if there's a vertical overlap, they are a multi-unit residential, and we will be returning to that and talk a little bit more about that a little bit later. Then there are 4 report tabs. So there are supporting role tabs, and that is the report guide, that is here. And over here, we have 3 more. And I'll go in and I'll show you what's in these tabs. So the first supporting tab, starting with the supporting role tabs now, going back down, is we have all the items that are available in the report are defined here, what to do and going down here. And I'll come back to that in more detail. I'm going to do a quick overview here, and then I'm going to come back to this. And you will see when we refer to the reports later, I'll come back to this. This is, you can see here, the title is D and B. And so these are how to fill in the areas in the A in the sections of the compliance reports. Then over here, down here in the Hot 2000 data, is a sheet that shows you where, when you're pulling out data, you will notice the columns in the workbooks, in the calculators, are labeled A, B, C, D, E, F, and so on and so forth. And all that information is here in the Hot 2000 tab, Data tab, and so you can see where to pull the information from. And so reference house fuel consumption is your last ones, and you will see those here. So if you're wondering where to get these out of the Hot 2000 reports, this is where you're going to look. This is your step code levels. And this is where all the data is for all the formulas. So this is all linked, and these are all the tables that are used to auto-calculate the metrics and compare them to the requirements in the code to see if the house that you're modeling, the building that you're modeling, complies with step code. And so, for example, you'll see here we have a helper, and that's just a label helper, and it's not part of the formal tables in the code. But then we start with this one. We have step code, step level, climate zone, air tightness, so on and so forth across the top here. And we're still calling this percent TEDI. That is the way it is in there, but it's now the percent BETRH metric. And so these are the percentages. So for the step level, for this climate zone here, you can see the air tightness and the percent LTRH and the TEDI requirements, so on and so forth. These are the adjusted TEDI requirements in here, because we're now adjusting by heating degree days. You'll notice that there's no MEUI here, no MEUI, so to speak. And that's in the next table here. And that's because it needs its own separate table, because it's dependent on not only climate zone, but also whether there is cooling or not cooling in the building that's being modeled. So we need a separate table for that. And then you'll see the steps in here, and also the MEUI, unlike the other ones back here. You will see that the MEUI is also dependent on the floor area of the house. So a different table was created to link that. And these are just references in here. If you're wondering, this is open to have a look at for sure. And so instead of going into the code, for this table to work in the heating degree day adjusted TEDI, which we'll get to once we get into the calculators, here you'll see some minus numbers, minus 15, minus 20, minus 30. That's because the appropriate heating degree days has not yet been entered in the calculator. So these numbers are just not making sense. And then we've got 0, 10, 0, 5, and then also we're back to the minuses. So we need to enter the appropriate heating degree day value into the calculators for these numbers to make sense. And these numbers are only valid for the heating degree days that you enter. So if you were to put in 2650, which is Victoria, then you are in this climate zone, and only these numbers for this climate zone would be valid. These numbers down here for these climate zones would not be valid. You'll still see entries in there, but of course they wouldn't be valid because they are in climate zone 5, 6, 7, A, B, and 8. And we've only entered the heating degree days for climate zone 4, which is up to 3,000 heating degree days. That's a little bit of an overview there. And again, these are just selectors so that our linking and our formulas will work. And that's what's here. So, and then if you want to know how the metrics and the requirements, when you're trying to comply, how to round to decimal points, then there's your rounding calculations notes are in here, how to round if 10th. So for example, this bullet here says if the 10th decimal is less than such and such, we get rounded to a whole number, right? So 26.49 is rounded down to 26. So there is no decimal rounding. Whereas in this bullet down here for a different metric, you'll see that we round to the nearest decimal point, single decimal point. So you'll find all that in there. So those are the supporting role tabs as a quick overview. So the calculator tabs that use all this data in the step code levels here, the two calculator tabs are your single family homes and MEURB calculator. And they look like this, and I'm sure many of you have already seen this. And so you enter data in here, heating flow above grade, heated floor area above and below grade, the base loads, annual energy consumption, and the ERS Reference House ERS, which is the annual energy consumption for the reference house. And so this calculates you will see up here where it says percent LTRH and MEUI. So basically the information that is here calculates the percent LTRH and the MEUI. Of course, the MEUI will also use this floor area, which is totaled here because it's a normalized metric based on per square meter. Here you put in the building envelope surface area, the air changes per hour, and the normalized leakage area. Now the normalized leakage area and the building envelope surface area is not really yet used as part of the requirements, but we have it there because there's a lot of discussion about using other metrics other than air changes per hour and perhaps normalized leakage area, normalized leakage ratio, and equivalent leakage area. There's other metrics, ways to represent the leakage in the cold air or air that needs to be heated, conditioned as it comes into the building from leakage. And some of these are perhaps more or less appropriate depending on building size and geometry and this and that. It's all under discussion now. For now, in the code, we are using air changes per hour. Then we have auxiliary energy required, which is a metric for the TEDI. And then we have the proposed and reference house. And this is also like TEDI, but it's to calculate the percent, the building envelope percent better to the reference house metric with reference house mechanicals. So I'll be showing that as a second portion. And then we need to know the design cooling load, the cooling capacity, and this is the percent of the building cooled. And if you remember back here, I was saying for the MEUI calculation, we need to know here whether it's not more than 50%, or down here, where we are more than 50%. So you can see it down here, right here. Goes from not more to more. And so those two. And so back here, we need to know whether it's more or less than 50%. So these numbers need to be entered. And for the calculator to work, you need to enter them. It's important that we don't forget. We get questions about why didn't the MEUI work and why can't we get a value? And so the reason is, so we put this in here and make sure you had to have it in here to calculate the right value. So it just doesn't default to one or the other. And so that's why your MEUI wouldn't work. Calculation wouldn't work if you haven't entered those numbers. And then the design heat loss, we need that for calculation that also happens to the reports. It's not current in the code right now, but it was PTL. That was its acronym. And it was basically dependent on the size of the heating system. Then the estimated greenhouse gases, and then the fuel consumptions are all in here. So M, MNO, P, Q, and R. So these red numbers, not these column letters, but these column letters here is what is referred to in the HOT 2000 data. So those ones I just showed you are right in here. And so you get that out of the report in HOT 2000 when you scroll down to the bottom of the full house report in this case. And so you will find those there. So that's the calculator. This is where you put in your heating degree days. And I will be running through one of these examples to calculate through this. This is where you see the data come in. And I must mention, I forgot to mention, so the blue here is for the proposed and the yellow is your as-built. Same up here for the proposed and the as-built. And you're going to put your P file number and your N file number in here. And so down here, and these auto-populate. This all auto-populates. There's nothing to do down here. There's nothing to do here. And so you will populate in here. And I'll show you how to do that. This is where you select your step number. And this is where you enter your heating degree. This is where you enter your heating degree days here in this yellow highlighted cell. And down here is a whole bunch of other information. And you can see here it says section F, other energy modeling metrics, and that refers to the reports that are submitted to the authority having jurisdiction. The attached non-MURB calculator. So again, non-MURB. So if you have side-by-side duplex or townhomes and there is no vertical overlap. So by vertical overlap, they're called interlocking. Sometimes we have more than just a simple interlock on the vertical overlap, but if you have a vertical overlap, that's defined by HOT 2000 by EnerGuide rating system as a multi-unit residential building, even if it's a 6-inch, a 4-inch, a half-inch overlap. They don't distinguish between that. Of course, common sense might rule on the half-inch there, but and you will notice that the this calculator allows up to 10 inputs. So you could have a townhome that has 10 side-by-side units. And that's more than ample. Occasionally, we're now seeing that you have extras, so then you're going to have to double up and have a second workbook open, and then you can put the sum total of a couple of units in each row here, and you could really, have you could have as many side-by-side units as you wanted with the workbooks, and then just transferring the totals, which come along the bottoms here, into each row. So you could go on basically forever. So this is set up exactly the same way as you'll see as this workbook here, as the single family workbook. They are the same. I'm going down small, but just to give a picture, a bird's eye view here, this whole structure, except for the only difference is here, there's one row for the proposed, one row for the as-built, and in the attached non-MURB calculator, there is a lot of rows for the proposed and a lot of rows, 10 rows for the as-built. So those are the calculators. And so now we'll go to the reports. So here's the pre-construction report, and they are section A, section B, section C, section D, E, and F. And then there's some optional in G. So if you remember over here on the attached non-MURB or on the single family, either one went down into here and it says, let's make this a bit bigger, sorry about that, there we are. So it says section F right here, right? Other energy modeling metrics. Well, that will populate in here and it self-populates. It just auto-populates. So that's section F. So as you go back and forth between your reports, here's D. Up here, you'll see D. And we'll go back here. And certainly E, you'll have to complete manually. Well, actually the P file numbers auto-populate. But here's section D, and this is where you see whether you comply or not. And so those are the section numbers. So these section numbers, as I was mentioning earlier, also if you go down now to the report guide down here, you will notice that here, A, project information, and we've got building permit, builder, so on and so forth, project information, building permit number, builder, project address. So that's all referenced in there quite easily. And whoops, wrong report. So you just go down here and you fill this in as per the instructions here. Now the instructions on the report guide, I'm flicking around rather quickly, but I'm back and forth. This is the report guide we're on. So in the report guide, you will notice that there are, on the right, there are two different rows. One is a little bit grayed. The second one is a little bit grayed. So the first one gives you a description of what this field is about, what you're filling into the field. And the second one tells us what we must do. So data must be entered manually in the pre-construction report. So we got to enter something. However, it auto-populates in the as-built report. So what we enter in the pre-construction auto-populates in the as-built report. So that's the building permit number if it's available. And so we're just going to put something in there, some gibberish, and we will note that the same gibberish shows up in the as-built report, which is next door here. So I notice I'm switching back and forth between the pre-construction and the as-built report. So let's take this back out. And then go to this one, and you'll notice it's gone. So that's how to use this report guide. And it's got climate zone, and it describes everything that we need to know on how to fill out the reports. Again, just to reemphasize, on the right, the top is a description, and the place in a shaded in a very light gray is the instructions on exactly what we're to do there and how to do it. So we're not left not knowing why we're filling something in or what it is, and then also the instructions on how to do it. So some areas in the report like this, they will auto-populate on the next report, but we're also allowed to overwrite it on the as-built report. So that is the case with the building characteristic summary here in section B, this area here. The reason for it is that sometimes construction changes from building permit and to occupancy permit stage to the as-built when it's built. And so we need to be able to overwrite and write in the new assembly, whatever that new assembly was. So all of these fields here can be overwritten. Other fields cannot be overwritten, so you just won't be able to get into them, and they're locked. They're locked so because there's so much information here. I know that some supporting Excel calculator workbooks, they're left open so we can actually see what the formulas are in that workbook, and we can kind of reverse engineer them and know what they're all about and where stuff is coming from. I myself quite like that, and I do take some time sometimes to see how those workbooks are constructed, and they come from EnerCan and other places for various things. They have one for calculating the energy factor for hot water heaters and for example. So, but we don't do that here, and the reason is that there is so much information. It's so easy to select a cell and turn around. Somebody comes into my office and I accidentally brush the keyboard, and I enter a different number into a cell, and all of a sudden, lo and behold, the formula is gone, and I don't know what's going on. This workbook doesn't work anymore. So that's why as you can tell, there's a lot of formulas in the background for these workbooks. So those are the reports. And then there's the as-built report, and they're filled out. And again, these reports, all this information is linked back to this calculator or this calculator. And then if you're looking for the information out of HOT 2000, where to find it, it's on this tab. All the step code information is on this tab, and it's just chock or block full of information. And then there's this information around rounding calculations. So that is it for this section for the tab overview. The next section will be B, and we're going to actually model a file. So we're going to move into section B, model the HOT 2000 file for the percent building envelope lower than reference house file. And we're going to find the instruction set for doing this. We're going to use the one in Appendix 8 here, but it's also in Section 6. Section 6 in the manual is for modeling townhomes or attached buildings, duplexes, townhomes. And but it's just I'm going to use Appendix 8 because we're not going to go into the townhomes yet, but it's the same instructions either way. So here we have the instructions. Here we have Appendix 8, and if we so the nice thing about this manual, this would be the manual that Peter has or will be giving you the links to go find this manual. The manual, the table of contents, it's quite nice. You can go, we're looking for Appendix 8. There it is, right there, Appendix 8. And you'll notice the pointy finger as we move, and that means that it's live linked. And so we just click on that, and then Bob's your uncle. So we've got a definition of what it is. There's a formula in here, how to calculate it. And what we're looking for is we're looking for the modifications here the proposed house, or the modifications to the as-built house, either or. And so we're going to go through this, and part A is the ventilation, and then we're going to change the space heating, and then we're going to change the domestic hot water system. And we're setting this so that the reference house and the proposed house will model the same. The only thing that will be different is the air tightness and the envelope. And so the mechanical systems, we're taking any heat gains out of having different mechanical systems. For example, if you have a natural gas, low efficiency hot water tank in there, there's a lot of heat gains that comes into the house that wouldn't necessarily come in the reference model. If we model a heat pump, again, the reference model models baseboard, so different heat gains. So where we're pulling the data out of HOT 2000 to calculate the metric, we want to make sure that the heating systems, the occupants, all that are the same, so that the internal heat gains are the same for both the proposed and the reference house. And that way we get a truer representation of the heat loss. It's not a totally true representation, but it's as close as we can get at this point. Do note that reference house places the windows in different orientations. It spreads them 25% on each orientation. And so really the solar heat gains that comes into the house is different between what we've modeled in the reference house. And so that will be a little bit different between the houses. And well, we just have to work with that. So here we go on modeling the ventilation systems. So what we do is, I'm just looking for my, I'm going to pull, I use Total Commander here, and you'll see down at the bottom here, I've got all my files here, and we are going to be using the P file, and so I'm going to open that, and you can also see in here that I've labeled files BETRH, end file BETRH, end file reference. So there's various different ways you can label these files so that you know what the differences are. End file AB, end file proposed, whatever works for your system. So certainly for the BETRH, I find might as well write BETRH, just 2 more letters than writing reference, REF, but it makes sense to me. We also use a 3-character version number here in-house. It's something that you may want to look at. You'll notice that we have a code library right here, and we may have several code libraries for a house model, and one will have exterior insulation, another one won't have, another one will have triple glazed as opposed to double glazed, and so on and so forth. And so one of the characters in our 3-character version number goes to which code library we're using for that house. Another character goes towards the geometry. So sometimes windows change, sometimes we move from attics to vaults. It's becoming more popular to spray foam up under the roof sheathing, and so we'll have version 1 point something being just attics, version 2 point something being vaults, and so on and so forth. And then the 3rd character we use for heating systems, mechanical systems, really hot water, ventilation, and heating systems, and also for insulation slab undergrade, because that's not modeled in the code library. So you may want to look at putting different version numbers together as you see fit. So right now I've got a file open, and I'm going to show you what that file is. I'm just going to bring it over. Okay, and we're going to start here, modification of the proposed house. So in this instruction set in Appendix 8, again, are all these definitions. So we're going to start here, and we're going to start with the ventilation system. So with the ventilation system, so the first thing we're going to do is we're going to save this file. And this is the P file proposed. And we're going to call this dash DETRH. And then I'm going to put my initials on it, NAA, so we know who's doing this file. We have a few modelers in house here, so, and then we patiently wait for this to come through. So we go down to the ventilation system, and what this says is, in the whole house, components tab set all fans to non-applicable, including an HRV, then set the fan type to utility, the exhaust and air supply airflow rates according to code level ventilation levels. And then in the supplemental components tab, we're going to set the dryer to NA, and except the dryer, we're going to take everything else out and we're going to leave the dryer. And then we're going to run the full house report and we're going to look for this information down here. So let's do that. So we're going to go to whole house components up here. We've got a couple of extra bathroom fans. We've got a utility fan. So this is our supply air coming in at 28 liters per second. I believe it's 60 CFM. I'm going to change this because I don't mind the metric, but I'm still a little bit more comfortable in the imperial. But I'm going to show you a calculation that's a little bit later. It is 60 CFM and 30. So we're going to set these two bathroom fans to non-applicable. And then we're going to go into the utility fan and we're just going to reset that to 60. Not that it matters. I wouldn't do it if I'm just doing a file, but for myself, 59.9999 is close enough for our purposes, but just to be clear here. And then we're gonna leave this fan power at default for now. You can turn it on, off or on the switch. We're going to be coming back to that. So that's that. Then we're going to go to the supplemental components. We have the dryer modeled, and then we're going to get rid of this range hood. And so this is NA. This just ensures, again, that the reference house and the proposed house are the same. It's just insurance. So now, whoops. So now we're going to go here. And we're going to run the full house report for the ERS Reference House, for the reference house. And we're going to go to this tab and we're going to note the fan power, the air flow supply, and exhaust rates down here. Okay, so let's do that. So we're going to go to the report. We're going to go to the full house report now. And we're going to go to the reference house. And thankfully it shows up. I was getting some errors earlier today when I was trying to go into the report. So we're going to scroll down here, air leakage and mechanical ventilation. Here's the new ERS ventilation data, same as what's shown over here on the right. And so now it shows an exhaust rate of 34.69 liters per second. So 34.69 liters per second. I forgot to show this report in Imperial. It'd be a bit easier, but that's okay. I'll switch the other one back. And this one is 80.48 watts. So we're going to write that down, 80.48 watts. And so because of the internal heat gains, all fans that are running, all mechanical equipment, when it runs, the power goes to heat. And so we want to go back to our house. We want to go to the ventilation, the whole house components. We're going to go into here and we're going to set this to 80.48, which we remembered, 48. And there's, oh, we can't get 4.8, so we're going to round it up to 5. And then I'm going to, because where are we? There we are. I'm going to go back to metric. here and then go back to my ventilation. And I'm going to go in here and you notice it's 28.3168. 28.3168. You may say, well, so there's a difference between the reference and the proposed house, but there actually isn't. So if we go to our reports and we go to our full house report, and a house with standard operating conditions, not the reference house this time, we shall notice right here, we've got 34.69, which is exactly the same as it was in the reference house. And we've now changed our power in a proposed file. So you know that it does say 8.5, not 8.48, which it says in the reference file, but that's as close as we can get it. So, but why are we in the ventilation area at 28 point some liters per second, and yet the report for the house says that we've actually got an airflow supply rate of 34.69 liters per second. So the difference is because of this. So let's go back to our ventilation. And we've got 28.3168. This is where I'm not that great at, I don't like all these decimal points, but it is what we have to work with. So 28.3168. And I'm just going to put my picture back in on the screen here, so you can see when I'm looking away, I'm looking down calculating, so you can kind of see when I do that. So the reason for that is we have a rule set here, and where are we? Page 13. Let's go Control Home. So this is the EnerGuide Rating System Rule Sets Reference Document version 15.6. You would have been able to have downloaded this with version 11.6 and version 15.6 of ERS, 11.6 of HOT 2000. This was one of the downloadable documents that we could get. I suggest you go back and get it if you don't have it. And it's of great interest. So where we want to go here, this tells how the reference file is modeled in HOT 2000. So we're going to go down. We were on page 13, but the other way to find it is to go down here, house with household operating conditions. EnerGuide Rating System Reference House. That's what we want here. So you'll see here, EnerGuide Rating System Reference House is here. And we want the ventilation system. So we are right here at 247. So again, you'll notice the finger, the pointy finger that comes up as we go across. So this is linked. So we click to that and we come across and we find here, it says 247 ventilation house. Well, so where we are here, I'm just going to expand this a little bit bigger so we can all see it a little bit easier. The evaluated house contains whole house ventilation systems only. So it's not about the supplemental. This is, remember, this is for the reference house here that we're reading. This whole section 2.4 is the reference house. So in this case, the reference house is modeled as follows. Whole house ventilation system is 480 minutes per day. I mean, code asks us for 24/7, but HOT 2000 models 480 minutes per day. And it does it in the following way. I'm going to skip a little bit. Ventilator type fan utility puts in a utility, and the exhaust is set to the sum of the evaluated whole house fan's airflow rate. So in other words, it's equal to what we put in there. But if the sum is less than 22 liters per second, so if you put in 15 liters per second, it's going to model 22 liters per second. It's just going to keep defaulting. You put in 21 liters per second, it's going to default to 22. You put in 28 liters per second, it's going to model 28 liters per second, except it isn't quite. As we saw, we modeled 28.3168 liters per second. Excuse all the decimal points, but I want to keep them for now. And the reason why we're getting 36 point some is note that the operation of the schedule of 480 minutes per day is split into two different flow rates and schedules as follows. So what this says is there's a certain flow rate for 408 minutes. So if we model 60 CFM or 28.3168 liters per second, that is the flow rate for 408 minutes of those 480. The other 72 minutes, the flow rate is 2.5 times that 28.3168, and to account for the high speed ventilation. So lo and behold, if we take 28.3128 and just, I don't have this written down, you kind of have to follow, but if you take 28.3168 and you multiply that times 408 minutes and multiply it times 60 seconds per minute, and you get, we get 693,195 and a bunch of decimal points, liters delivered in that time. If you now take 28.3168 liters per second and multiply it times 2.5, because now we're going to, for an additional 72 minutes, we're going to be running at 2.5 times that. And you do the same calculation. So 28 point whatever times 2.5 times 72 minutes times 60 seconds per minute, you're going to get so and so many liters that have been delivered by the ventilation system in the 72 minutes. Add that amount of liters to the liters that were delivered in 408 minutes, and then divide it by the total amount of minutes in 480 minutes per day. So 480 times 60. So you're going to divide that by 480 times 60, which is 480, 60 times. So 28,800 seconds. So what your total liters delivered in 480 minutes, you're going to divide it by 28,800 seconds. And you are going to come to exactly that value that we had here in this report for either the proposed or the reference house. Either way, it's going to show up, and it is going to equal, where are you? 34.69 liters per second. So you're going to want to prove that out yourselves out there. If you have any doubt about it, it does work out. I've done it a number of times. So you just kind of need to get the math right and get it into seconds. I prefer working in CFM because then I don't have to divide it by the seconds and I don't need all those dratted decimal points. But that's the way this file is. I guess you could model 28 liters per second, but then you're going to get a bunch of decimal points on the other end. So that is why we look in. And so when we have that, we know that when we do that double check, we know that this is actually correct. And then again, we've changed the power to what the reference power was. It started out around 40 watts. And it's now 80 watts. So now we've done the ventilation portion. So now we need to, that's the difficult portion. So what I've done here in the instruction set, what's in the instruction set, so that ratio is actually 1.225. So if we take 28.3, 1.225 times, we get 34.6, which is 66. So that's about where we were. And it gives the example of the screenshot above, where in the report it shows 39.2, and then 32 liters per second is what would be modeled in the model right here. Over here, I'm on the left here. Showing that, so that's 32. So we've done the math for you here, and so you can just see that. But that's how it's That's how it's done. The space heating system, we're going to set to electric baseboards. We've got a heat pump. Let's get rid of that. Additional openings. Let's get rid of additional openings. No radiant heating. And we have no supplementals. So if there were supplemental systems, we're going to get rid of them. Any radiant heating, it all goes. Clear, clear, 0. Oh, I guess it doesn't take a 0. Okay, so that's what this box looks like. And so now we just have the electric baseboards calculated, fans, pumps set to auto. It's actually non-applicable. Doesn't matter whether you do non-applicable. The instructions does say calculated set type 2, non-deselect, deselect set fans and pumps to non-applicable here. So you want to do that just because electric baseboards have no fans to distribute the heat. So let's get rid of that load. They're not in the reference house. Now we're going to move to the domestic hot water, and we're going to set this to electricity, which it already was. I thought I used to have natural gas in this file. Just a conventional tank. We set it to 50 gallons, 50 US gallons, energy factor 0.7, input capacity 3,000 watts. And I found when we were doing some iterations on how to set this, we found that by using the standby heat loss down in here, was a bit accurate. The energy factor moved around. You'll notice that standby heat loss is now, you can just see it, faint gray in here. It's 0.98, and we want that 0.87, is it? Yeah, 0.87. So we're going to run the reference house again, run the full reference house report. Go to the domestic hot water and note the standby heat loss rate. And that's 77.86. So we're going to do that. So we're going to go back to the full house report. We're going to go to the reference house. And we're going to go down to the domestic hot water system now, which is down here in the full house report. And you notice that the standby heat loss rate is 77.86. So we want to note that, and that also here gives a calculated energy factor of 0.87. So that's where the 0.87 comes from. Domestic hot water, we are 79.8. And because we can only get 1 decimal point, again, we've got to round up ourselves. And you'll notice that this is really close. It's 868 instead of 87. So what happens when we go to 80? 867, it's getting worse, 79.8. It's pretty darn close because you can't get that extra 1 in. So we're getting in here, and it does come out to, here's that 98%. If you went back into the reports, it shows that. So it does come out to an energy factor of 0.87, and it always does now, noticed. And so we could do this and be correct and 0.87 and just put that in here. We do want the 3,000 capacity, yeah, so and that's the energy factor for that. So that's how you set the domestic hot water. And then we are basically done. that's it. We have now done the BETRH file. So we just save this. And again, being quite patient with Hot 2000. And we save it. So one of the other things I noticed here, the difference between SF, single family home and MEURB is if we go back to the rule set, you can read this for yourself. So for the ventilation, when you go down, contains a mix of whole house ventilation systems and supplemental fans. You can read further down here and you'll see how it changes when you've got different units, and like when you have multi-unit residential, it just, you know, there's just all these different scenarios here. So if what you model is reported differently in the reference house or whole house reports, this is where you're going to look for that. So you can see all that here. So that's it for section B. And so next we are going to extract data from Hot 2000 and we're going to enter it into the calculators. So now we're going to do section C. We're going to extract the data from Hot 2000 and we're going to enter it into the calculators. And for this, we're going to look at the AC or no AC, the 50% rule. There's some differences in the MEURB and the base loads to the single family home that you've got to remember to account for. And then we're going to look a little bit at the townhomes, section 6 in the manual. Same manual we were in for appendix 8 for the last section for modeling the BETRH, but now we're going to go to the townhome section 6. And we're going to look at the ACH averaging and using the adjusted ACH. And Peter had a slide on that. We're going to look at a little bit of CGSB versus as operated. This is something that's little known out there. It doesn't, when you're doing your P file, doing CGSB versus as operated, it really doesn't matter what you use, and I'll show you why that is. And then a little bit on our effective calculations and on how to sum that up. There are places that we can get this out of the reports for Hot 2000, but there's another way to do it if you do want to calculate it manually. You can set something up on a spreadsheet to do that. So let's get into this. This is about 30 minutes as well. I noticed the last section B was 30 minutes, so we're sitting about 30 and 30. We'll try and keep this one to 30 minutes as well, so we can get complete in it within 2 hours here. So we have, I'm going to reach over here and I'm going to bring my Hot 2000 file in. Then I'm going to shrink this a little bit. Let's get some more tabs showing here. And we're going to start extracting some data. So in this file, I've got my P file, and I also have in this file I have my BETRH file. So you can see here's the BETRH file, and here's just the regular P file. So the proposed house. So I've got both my files here in the same instance of Hot 2000, and you can open them in 2 instances of Hot 2000. It doesn't matter as long as you remember. You can have the same instance as long as you remember to select on the right file, which you would have to do in different instances as well. So we're gonna start with the single family home calculator here, and we're just gonna come up a little bit here. So in the specifications tab down here, we have the floor area, which is down here. And do remember that over here on this tab, we do have if you're lost for where you get that from. So again, here is the floor area, and here is the tab where the dialog box that we're looking at. This is the dialog box that we're looking at over here, right? So so you can go to the Hot 2000 data tab if you need the help on that. Oops, I hate leaving ranges marked up in spreadsheets. Okay, so off we go. So above grade is 206.2 and below grade is 118.5. And so that totals to 324.70. And then we're going to hit our Alt-C to calculate. And so I just hit Alt-C on the calculator. And we're going to want this number here, and we're going to want this number here. And so that's the reference house and the house of standard operating conditions and the base loads. And so the base loads for this file, where is the base loads? There it is, right here. So it's here, the second one up from the bottom, 25.62. So why do I bring note to that? Well, if you're modeling a secondary suite, you're modeling a MEURB, and this base loads is going to be different here. It's going to be a different amount if you're modeling a 3-unit MEURB, a 4, 5, 6. So you need to know what this base loads is. The total AEC down here is 50.84. So we're just going to enter that in here, 50.84. And then the ERS Reference House is 83.47. 83.47. And so now we're going to go into the full house report. So we'll close this out. By the way, another way to get into that report is to go calculate here. So there you see the Alt-C shortcut that I used on the keyboard. It brings up the same for really new users of Hot 2000 that may not have seen this. It brings up the same dialog box. So Alt-C on your keyboard or calculate. I'm a big fan of keyboard shortcuts in many things I do. So next we're going to go to our full house report for, not the reference house, but for the house with standard operating conditions. We're going to bring that up here. So that is one of the dilemmas with having several windows within one instance of Hot 2000, is things do start to hide a little bit. We might have to look for them to find them. So what are we looking for first? The building envelope surface area. So that is in the air leakage and mechanical ventilation. So there, right here is the building envelope surface area. And it comes right after all the envelope stuff here. You know, your basement walls, your above grade walls and envelope. So 61287. 61287. And we're going to move over a little bit. And we are modeled at, so that we can see the next one is 2.5 ACH. We are modeled at 2.5 ACH, and you'll notice this is the reference house line. I often don't fill much into this reference house line unless I have to, but it models at 2.5. And for step 3, which is many of the houses we do, it models at 2.5. This one I just want to do the same as the reference house for now. And then the air tightness NLA at 10 pascals in centimeters squared per meter squared. There we are right here. Here's the normalized leakage area at 10 pascals. So many centimeters squared per meter squared. So we're going to put that in as 1.2736. Then we're going to go and we're going to look for our auxiliary energy supplied, and that's down a little ways. And we find it under the annual space heating summary. Again, if you can't find these in the reports, go to the Hot 2000 data tab on the workbook. And we see the auxiliary energy required right here, and that's 29,813 megajoules. So 29,813 megajoules, and this is to calculate the TEDI. And then I'm just going to shrink a little bit here. These next two come from the BETRH file, so I'm going to leave those alone for now. And I'm just going to, while I'm in this one, I might as well, while I'm in this report, I might as well take out some other numbers out of it. So the design heat loss, we have right below where we took out the auxiliary energy required, and we have the design heat loss and the design cooling load. We have both of them. So the design heat loss is 7,100 watts. So in other words, 7,100 watts at 7.1 kilowatts. So that is 7.1 kilojoules of energy per second going out through the envelope that our space heating system has to replace when it is -4 degrees centigrade outside. And it's our set point is what, 21 degrees inside. So again, so 7,100 joules per second of energy is we're losing it, either through the windows, through the envelope, through air leakage. And so this is what needs to be supplied by the heating system. And further to that, the design cooling load happens in July, and when it's 24 degrees centigrade outside. And so if we have an AC unit, it has to be able to supply 4,385 joules per second, or approximately 4.4 kilowatts capacity system. So this is called the capacity, 7.1 kilowatts and 4.4 kilowatt systems is how you would size it for the whole house. So we're going to put these numbers in here. So the design heat loss was 7,100, and the cooling load was 4,385. And so then what we need to find is the cooling system capacity. Now, if you don't have AC, that just goes to 0. You just set this at 0 if there's no AC. So if you got a natural gas boiler and nothing else, that's it. You set that to 0. But here we've got a heat pump. So we do have an air conditioning system, and we see that here. And so here is the capacity of that system. And so that's what we're looking for. We're looking for the capacity of the cooling system here. And it is 4848. So we'll put this in here. And interestingly, 4848. So it has got a capacity that at its maximum capacity, it is going to basically meet this cooling load of 4,300, 4,400 watts, which is just great. So that's nicely sized. Then while we're in here as well, we might as well take some other data out of here. So we're going to go down and we're going to look for, here's the greenhouse gases right here, estimated greenhouse gas emissions, 0.15 tons per year, 0.157 tons per year. And then we're going to go down here, and we are only electricity in this file. So this file here, estimated annual fuel consumption summary. If we're using propane, natural gas, coal, wood, it will all show up in here. And so the total at the very right side of the column here of electrical energy in kilowatt hours now, not in megajoules or gigajoules or kilojoules, it's in kilowatt hours, is 14,121. So we're going to put that in here, 14,121. And we have no natural gas consumption. However, if we, for example, let's look at this data file down here. And on this one here, you will see there's both natural gas and electricity. So this one has natural gas, and the blue area down here at the very end says we have 518.1 what? Cubic meters. So 518.1 cubic meters. So if that was our file, we would be back here and we would put in 518.1 cubic meters. And you'll notice that the units here, kilowatt hours for electricity, cubic meters here, propane consumption next door here is liters. So these units are all set the same as in the HOT 2000 report. So you can just pull them straight out. And then because we don't have any more fuels on this file actually, so this is 0, 0, 0, and we'll just put zeros in here. Or you can leave them blank. So I like to put zeros. I like to put entries into fields, even if they don't get any, either non-applicable or zero. It reminds me that I've paid attention to that field and I haven't missed anything when I scan. I look for the blue, and I don't see any blue, so I've got all my fields, I've got all my information. So now I've got to deal with the building envelope percent better with reference house metrics. So I need the proposed auxiliary energy and the reference house auxiliary energy. And this comes from the BETRH file. So let's just make this smaller. So this is the P file, and down here, oh, here we have it. We'll make this bigger. This is the BETRH file, so we'll make that one active. And again, we're going to go to full house, and now we've got to do 2 full house files. And first of all, we'll do the proposed or the as-built for the actual house. And we scroll down, 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 a bit of Johnny Cash in there. And here we have auxiliary energy required, 31,062 for the proposed 31,062. And then for the reference house, we're going to get another report. And here we are again. So the annual space heating summary, again, energy required, 39,447. 39,447. So that's great. So when we remove the heat pump, you know, any effects from the heat pump, we basically have a better envelope. So you'll see here, the heat pump here, when we look at this, we have 50.84 gigajoules and 83.47. So what's that? A 50% at least, and over 50%. 50% better would be 75 gigajoules over here, and we're well above that. And then here, we remove the heat pump, but we're still better. We're better by, oh, probably about a third better again, so 30% up on the proposed house. So, you know, but percentages work off of the reference house. So basically, we're 8,000 better than the proposed house. So it's 8,000 divided by 39, not 8,000 divided by 31,000. That gives us the percentage. So a bit smaller percentage here. 8 divided by 40 is what, 20%? In that range, I would expect once the numbers are. So let's just say we're going to step 3. So we go to step 3, we pick step 3 in here, and we need our climate zones. And so we put, it says right here, enter heating degree days in cell D30 to get the climate zone. So this is D30. So here it is here. And we're going to just go with Victoria, which has been 2650. At the time of recording this webinar, we just had a new version of HOT 2000 come out, 11.10. These are all being calculated in 11.8 actually. I didn't want to change the files from the start of the webinar, and so I just wanted to keep things from when we gave this webinar 3 times live. And I want to keep the files the same, but we now do have 11.10. So HOT 2000 Inner Guide came out with weather maps. And so there are a much broader distribution of heating degree days, but this was the average we were using for Victoria. So you will notice then that our cooling system capacity is down here as well. It auto-filled. We put it in up over here, right? The cooling system capacity up over here. And so, you know, watch what happens if you didn't put in the design cooling load. If we just delete this out of here, then this disappears. Down here, we still have 48, 48, but we can't tell whether we're 50% more or less. And you'll note that when we move down here for the mechanical energy use intensity, there's nothing filled in here. So right here, this is the MEUI. So if you have nothing here, that means that, you know, you're missing something somewhere. And so you need to know what's in there. Whoops, sorry. And so we need to go back up here and we need to fill that in, the 4385. Once we do that, we know that we have more than 50% of the cooling load of the building is satisfied. At that point, then again, this now fills in with the metric of 55. So with all these metrics filled in, boy, this house is just way off to the races. It passes on everything. So you see that 22 is better than 55, so on and so forth. And we're really off to the races. But let's see what happens if we go to a step 4. Let's see what happens. All of a sudden, we've got red in here now. We've got a bunch of red, and we have a fail at the bottom. And step code requirements met? No. So they're not met, and we're failing on the air tightness. Interestingly, we pass on the LTRH and the MEUI, and we pass on the 21% better. So let's go up here, and what is it for 1.5 for step 4? So let's put in 1.5. Lo and behold, now 1.5, and we pass, and we pass. So let's now go to step 5 and see what else we can turn red. Okay, so now not only on the air tightness do we fail, but we also fail on the envelope here. Certainly if we increase the air tightness, it's going to help our envelope metrics. But we've got a fair ways to go. We've got to get to 50% on the BETRH, or adjusted TEDI of 17, or the TEDI before they had the adjustment of 15. So really at 26s, we're a fair ways away, and at 50%, we're a long ways away, even when we go to 0.6. And I mean, I can put 0.6 in here. Oh, it's actually 1.0. I can put 1.0. And of course, if I modeled 1.0, these metrics would be smaller. We'd have less air leakage, so they would be much better. But still, we get a pass here. But we've got a long ways to go to get these. And so the air tightness itself wouldn't help. I don't believe we have an HRV in this house, and that's not going to help here either. For those of you who do Part 3 modeling, the HRV does count into the TEDI. For this house modeling, the HRV does not count. So there we are. So that's how this is all filled in here. Don't forget to fill in the P file number here. When you do it, we need that for the reports. You're going to see that for the reports. Sorry, I'm just going to go back to 10.5, and I'm going to go back to step 3 here, return our file so that we can use this for the reporting file. Okay, so when we, so the difference between the single family is that we got the area here. We really don't need it. We do need it for some calculations, but not for the metrics. So let's just, for example, take this and go into here and make sure I'm in the right place, and go V and go 2.4, and then go 550 and 2.3. And you'll notice down here we got 2.35. And when I click on this, you'll see everything highlighting here. So what it does is it takes the ACH multiplied times the surface area plus the ACH of the next row times the surface area, and so on and so forth. And then it divides it all by the total surface area down here. So we get an average 2.35. 2.2 and 2.4 and 400 should be changing it. 200 changes it. And so you can just see the average changes. So this also is for the NLA, the normalized leakage area. It happens in the same way. So getting this envelope surface area is really important in the attached units that you wanted there, for sure. So you want to do that. And this is what it looks like when it's all filled out. So this is would be for the townhome, where we're down here in the attached MEURB calculator, and you just fill it out for every unit. Here you can see the above grade. There is no below grade, so it must be slab on grade. Base loads for each one, and so on and so forth. And you will notice that I fill out, and I don't leave blanks. I put zeros in instead. Again, that's just, it's personal preference, however you do that. And so again, I just do it so I know I haven't missed anything except for what I'm supposed to miss, which is the next row. I've got 4 houses here. Let's remove this again. Let's go back to my agenda and let's have a look at what I've got here. So on the agenda, so the AC and no AC 50% rule. So we covered that here, down in here. And you get a break on the MEUI if you use cooling. In other words, it allows you to use a little bit more energy on the AEC up in here. This energy here, it allows you to be a little bit higher. So this metric here changes. So right now we've got 55. So watch what happens if we drop lower than half cooling system capacity. So if we go to 2000, which is less than half of 4,385, don't prove me a liar here. No, this is great. So now we've only got 50 instead of 55. So now we have to meet a tighter target, but we don't have to account for the extra cooling energy because cooling energy is accounted for in the total AEC energy, isn't it? So this is the whole house annual energy consumption. So if we add cooling to the energy of the house, this is going to go up, and step code says that you can add it in down here. So right now it's 50 for step 3, and here you'll notice the 2000 shows up and it says not more than 50%. So if we were to reverse this and go back, so I just undid it, and we're going to go back to our 4878 and our 48, sorry, here. And now we've gone from less than back to more than. And here we've gone from 50 back to 55. So it just, step code acknowledges that when you have cooling, you're going to use more energy, and that's just okay. So that's your AC and no AC. Differences between the MEURBs, again, are the base loads. So if you, there's my hot 2000 file. So in the specifications, building house, so we are a single family. If we go to a MEURB and we put in 3 units, for example, let's just say that we visit them all because I don't want an error. And then we do our Alt-C. You will see that our base loads are now 46.04. If we go to 2, we better only visit 2 units. We are now 30.69. So, and then once we go back to single family, we go back to 20, what is it, 25.62 right here. So you want to remember that the MEURB changes base loads. And so it also changes the number of occupants. So the internal heat gains will be different on a MEURB because you'll have fewer occupants per unit, more occupants for the whole building. So it's important that that's included in, and because there'll be greater heating gains. And that needs to be set for the BETRH file as well as for the regular proposed or as built file that you take values out of. So remember to set those. The townhome, I just did the ACH averaging file, so that's how that works. It's averaged, it's tested per unit. We're getting lots of questions about guarded and unguarded testing, and it's more definitions will be coming out over time as to what to use. Right now, ERS does not allow guarded tests, but that doesn't mean to say it's not in the future, and I might even want to erase that out of here because we want to keep this recording current, but it'll be current as long as you just don't take my word for it. Tomorrow it might be allowed. So I'm going to go to the CGSB, but first I'm going to just quickly on the R effective. So I create a chart right here like this for the R effective calculation. So for unit 1, these are for unit 1 or wall 1, wall 2, wall 3, wall 4, whatever. But if you are having to, for the reports, put in an effective R value for all the walls in the whole building, and you've got 10 units, just put in the R effectives here. And so I've set this up. I've got the equations for the U effective here. It's just the inverse. And then I put in the total area of the walls. And what happens is that this will average. And so if I change this to 50, you'll notice that the 3.9 down here, that this building effective down here changes as I change these. So 75, 100, things like that. So you'll notice that this changes. So if you remember from your building science course, and I do hope that you do, this is the heat loss equation. And it is the same if you use the U value instead of the R value, and it just goes up to the top. My preference often is to use the U value equation, the U times A times delta T, the temperature difference across the envelope. So I have such a sheet like this set up, and I use it. And then this here, equation here, and you see it all get colored up, is just based on this equation here. And that just comes from this equation. And then QT is equal to all the individual heat flows, which is all of these. Anyways, the equation comes to this. And so it's this equation when I click on here that you see all across here. And so you can set that up in an Excel sheet fairly easily. So that's the R effective. So a little bit about ACH. Let's expand this a little bit. So if you go back in Peter's slide presentation, if you want to understand how things are averaged, unit 1, unit 2, unit 3, and averaged, he's also written the equations in here for us. So it's a great summary slide to have a look at. I see a little number down here, 159. It's from a past presentation, but I imagine if it's not 159, it's going to be pretty darn close to 159 still. Be in that general area. if you want to reference it again. Might be easier than finding the place in my recordings. Okay, so let's have a look at airflow. Airflow through an orifice, through a crack, through a hole, through a tube. It's got an entry losses when it goes through, some turbulence happens. And so there's a pressure drop. There's energy that's taken up as flow goes through a crack. And we know that when air is moving at supersonic speeds, or an object is moving at supersonic speeds through the air, for example, an airplane, and we hear that crack, you know, as the jet breaks the sound barrier. So at our level, certainly at Mach levels, at greater than the speed of sound, we're dealing with air as a compressible fluid, and the equations are somewhat different. You can compress it. But for our purposes, we treat, you know, at our earthly conditions, we treat air as incompressible. And there's a small air that comes into the equations, but it's not important for the level of what we work with. And the equations are just way easier to work with. So really, we get an equation for airflow here of Q equals C times delta P times to the power of N. And just let me explain that. But first, let me just mention we've got a Q here, and this Q is in cubic meters per second. So this is the rate of airflow. But here on our effective RSI calculations, you'll notice we also have a Q here. So on this stuff, important not to mix it up. This is a different Q. This Q here stands for heat flow in watts or BTUs per hour. This Q stands for cubic meters per second. So that is the rate of flow, the volume rate of flow of the air through an orifice or orifices, or I don't know if it's orifici. I think it's orifices, probably with the S. So delta P is in pascals. So delta P is the pressure drop across the envelope. When we put our door fan kit in the door, we have a pressure difference. What our fan does is it induces a pressure difference from inside to outside, and we must test at delta P equal to 50, for example, and large part 3 buildings are to 75 pascals. N is a dimensional number, and it depends on, it depends on the characteristics of the crack distribution and size within the house. So it depends on that. And then C over here is just the constant that makes the equation work. And it also, so it depends also on the characteristics of the house. And we want Q to equal delta P to the power N on the other side. So we add a factor C to just to make sure that they equalize. So for those that have done a bit of math, you can follow along. For those that haven't, don't worry too much about this. I'm just going to show how this came about, because I like to, you know, if people want to know, this is how it is. We do some logarithmic arithmetic. So we use the log rules. If you do one thing on one side of the equation, you do the same thing on the other, and you're hunky-dory. So if you multiply times 2, 2Q, then you've got to put 2 times C times 2 times delta P. So you got to double both sides. In this case, we're going to use the logarithm. So we're going to do the log Q and the log of C times delta P to the N. And logarithmic rules say that the logarithm of 2 numbers multiplied together is the same as the log of the individual entries added together. So we do that. We go from here to here, and we get this. And then it further says in the log rules that the logarithm of something to the power exponent of something else is equal to that exponent times the log of that delta P. And so then this becomes this. And so now we're down here. And so this becomes then the full equation once we've worked it out. We've moved N times log P to the, you know, the front, and the log C to the back. And so we've changed it. And why do we do that? Well, down here, the equation of a straight line is something called mx plus b, m times x plus b, where over here you'll see that the slope is m, and so that's the slope of the line. The b is where it intersects the y-axis, so you have a y and an x-axis, and so the line slopes crosses the y-axis at b. It's called the y-intercept. And you will notice here that n up here is equivalent to m here, log delta p is equivalent to x, and log c is equivalent to b, and log q, of course, is y. So you can see that all here. Y is the log q, x is log delta p, slope is m, which is equal to n here, and y is the y-intercept is b, which is log c. So in graphical form, because you probably haven't grabbed all of that, in graphical form, it looks like this. When we plot it, if we plot log q and log delta p on regular graph paper, we get this. Or we could take some log graph paper and just plot q and delta p and get the identical thing. So this is what happens. So here we do our air tightness test. And we plot the test on here, and we want the value of q at 50 pascals, which is right here. And we come across and we find out what it is on the y-axis here, q, and that is however many CFM or liters per second we have leaking into the house total at 50 pascals. So the importance of n, which is the slope of the line, is that n equals 1, this is the slope. At n equals 0.5, this is the slope. And really, when you have larger holes for the same ACH at 50, note they're all the same at 50, but the hole size changes. It changes the slope of this line. Why does this matter? At 4 pascals is what hot 2000, when we extrapolate and find the CFM, or liters per second, at 4 pascals, that is the amount of air that hot 2000 uses to calculate how much heat it takes to condition that cold air coming in. So if we have a cool air day at say 3 degrees C, we have 3-degree air coming into the house and it has to be heated to 21 degrees, then we have this amount of 3-degree centigrade air that we have to heat. If we have larger holes, then we have more air that we have to heat here. So this makes sense for the same ACH at 50 with larger holes. There's less of them, they're just larger, so less resistance, so we get that airflow coming through. And if you actually look at the hole size and you look at the circumference, so it's really the total circumference that causes the resistance, which is why back at 50, we have the same amount of air leakage, whether it's the large holes or the small holes. I needed to think about this for a while for it to settle into my brain to see why it made sense. The key is, right up here in the middle is CGSB. It sets N to 0.68. CGSB standard is a standard for testing, and it will, tell you all about how to test guarded, unguarded tests, things like that. But also, it comes up with a number for a pre-test that if you haven't tested the house or the building yet, that you set N equal to 0.68, because you need to have an N value to be able to calculate an amount of air leakage, which would be right here, halfway in between the two. And so that many liters per second coming in at 3 degrees C, heated up to 21 degrees C, would be the energy that our heating system would have to supply and would go into the annual energy consumption, the AEC, that we enter in over here in our calculators. So this is the CGSB. So here we have CGSB, and we have the equivalent leakage area calculated at 780.6. I don't know if you can see that there. 780.6. This is calculated. We have 2.5 ACH at 50. So what that is saying is we have 2.5 ACH over here, however many CFM or liters per second that is over coming across the y-axis here, where we measure that. And then we take it down. So hot 2000 measures the heat it takes for the leakage area here. And that would be an equivalent leakage area, whole size, equivalent leakage in the whole house of 760. Now, if we go to as operated, this doesn't change. You can try it. It just doesn't change. So before we put in the air test data in here, when we set this here for the P file, it doesn't matter whether this is set to CGSB or as operated. And so it's sometimes easier just to set to CGSB calculated, because you keep getting this pain in the rear end error message when you set it to as operated, and it's will not calculate, so on and so forth. So the results will be exactly the same. So now you know what CGSB is, and you know how air tightness is calculated for this. So that's what it looks like. And so the other advantage of knowing this chart is when you're doing a mid-construction, when we are doing a mid-construction air tightness test, we look for the low-hanging fruit. The low-hanging fruit is the larger holes. And it's the larger holes that give us the more air leakage for a set amount of ACH. So when we find the larger hanging fruit, we start driving this line down, and we can see the effect of the sealing. The smaller the holes are, the less effect it has on our heating system. So don't sweat the small stuff, right? That's what it's saying. Don't sweat the small stuff yet. We are certainly testing houses where they are testing down like 0.4, 0.5, even somebody 0.23, but I'm not quite confident in the accuracy of our manometers and that sort of thing down at those levels. I mean, they're spray foaming, they're using aero barrier, the spray powder that they're spraying in, doing all sorts of stuff right now to get really airtight. Well, does it really make that much difference at the end of the day, whether you're 0.5 or 0.3? You just kind of want to, for our purposes for step code, you want to kind of look for the bigger stuff, and then help your builders get lower and lower. So that's what we do here. So that's the blurb and about air changes per hour. So that does it for section C. We're going to move into section D, which is about another 30 minutes. Okay, let's do section D, filling out the compliance reports. So what I like to do here is I go into the view menu and I create a new window. And so I've got two windows up, and then I half screen them across. So I have two. And so let me get, so here's a pre-construction report. Let's go up to the top. And then over here, just adjust a little bit at the bottom. Let's get rid of yada, yada, yada. And by the way, if you have a lot of tabs on the bottom, you can find them this way by going along, and you right mouse click here, and this when you're over those, and we are going to the single family home calculator. So so you can just see all sheets. You could also do that. It says right click, see all sheets. I guess that's what it's telling you to do, because if I click this, it doesn't work. So there we are. Right click and we can see them all, and you can pick your tab from there. Okay, so building permit numbers, section A. So do remember you have this report guide should you need the report guide. It tells you all about it, and you fill all this stuff out. So certainly we have a single attached. We have one dwelling unit. You'll notice that all this is filled in now. It wasn't before. We're less than 3,000, so that's climate zone 4. This is our heating degree days. This is our floor area. And so you will note that this changes. So we have 324.70, 324.70. And so let's just put 300 in there. And now we've got 418.50 both places. Yeah. So they are linked. Put in your version of Hot 2000, and I've been using 11.8. Climatic data location. I mean, I've been using Victoria. So you put that in there the best you can. So I realize, and we've had a lot of comments, that there just isn't a lot of room here to put stuff in. Do your best, do it short form. So 2x6, R16 OC, R20. You don't even need the word bat. You could have it. Building inspectors like that. 1/2-inch ply, R4 exterior bat, 1/2-inch rain screen. So RS. So you can see all the short forms, and then the headers. I hate that word headers because there's different headers. They're rim joists that we're talking about. They're not window headers, which are also called lintels, and headers are the word headers used in one other place. And so ceilings, foundation walls, slab is below. So you want to fill all this in, and we've created this one so that if you are changing, your values in here, if you have, say, triple glazed, you could do this. I love these subscripts and mucks up. I can't get out of them, but so we have US. Little I should be able to get a little I in there. And then I'm going to do backspace this and this. And you can, no, we're still subscript. Isn't that interesting? So it's a little hard to get out of the superscripts and subscripts. There we are. So that's great. So now we're large. So just undo there, and then you can go back like that, make the font a bit smaller, and you can have your triple glazed and double glazed windows if you have a mix of windows there, and you can write it in, and you can change your fonts on that as far as I know. So there is a way to do it, else write it out here. Just as long as they can see it, HSBF and SEER. If you're going to use EER for some systems, away you go. Just feel free to use that. And so you just keep filling this stuff in. Section D, you don't have to worry about when you're modeling Hot 2000, which this is all about, this webinar. Certainly if you were modeling section 9365, you'd worry about it. And I missed an area up here in section A. Remember to check the correct box. So this one, if you are doing 9365 and not complying, you do this one. 9365 and you are complying, you do this one, so on and so forth, and it tells you what sections to complete. So section C is out. And so you will note here that if we go down and we go over a couple of columns, and we just go over a little bit, that this looks an awful lot like this without all the colors. And down here, that's the word to pay attention to. If that's a no, it's in red. And so that's, you got to do something about that. So this house passes for 3. This is all autofill up here. You want to check off down here in these inner guide rating system. Megan Jewell, Efficiency Inc., company name, phone number, all your contact info. This self-populates. If you go over here, you will see that it self-populates. So let's just say we're on file 126. And you will notice that this one here now changed to file 126. So, okay, you want your SO number. So if you're with CHBA, what are they, 51? Your EA number, City Green is 79 for the SO, and your organization number. And then down here, these are all your other metrics where I put a lot of zeros in. But here's your normalized leakage area, you know, which we calculated from what we put in the CFM, rated greenhouse, and all that sort of stuff. Peak thermal load. So this was an older metric from a previous code issue. Not a previous code issue, a previous revision of the 2018 code. It was an earlier one, and it got taken out, and it was replaced with the BETRH, percent BETRH. And then down here is all your electricity, natural gas, fuel consumption. And then here, if it's built green or Energy Star for homes, do check the box. So that's how this works. And again, a lot of this self-fills over into the as-built report. Of course, this section is going to be totally, you know, independent. And you see it says no in red there. And that section auto-populates from right here on the right here on the single family. So one note is on these reports, it's really, really important to watch what happens when I change to a row house, non-MURB. So all of a sudden I don't have the floor area conditioned space here. I still got 2660, but so this up here, building type, tells it which calculator to pull the information from. So if I were, so no, there's no information here right now. If I go 200, 330, I've now got 530 cubic feet. This should be populating, and I'm not quite sure why it's not populating. It will on your sheets, I promise you that it will populate. Right now it's populating at a 0. I've been in and out of these sheets a lot, and you notice that I don't have them protected. So, so right now it is not wanting to populate to this 530, which it should be when I'm here, but it's got a 0. And if you go to the single detached, because I'm in the as-built. Sorry. So that's why it's me. So let's go back to the MURB, or the row house. I mean, there, 530. And you notice the heating degree days are gone. So let's go back to the attached here. And let's put in the heating degree days, 4,500. Boom, 4,500, and it's climate zone 6 appears here. And then this now changes to, we don't know what's required. See, it says 0. And now if we are step 4, then we put step 4 in here. And as soon as we put some metrics in here, step 4 will appear. There it is, step 4. And again, I'm in the, there we are, step 4. Okay, so now we got step 4, blank, 40, 40, 48, 4, blank, 40, 40, 48, 21.5, 21.5, and these are all zeros because we haven't filled it out yet. HDD 45, I changed that back to 2650, and that changes back. So they're linked, and they're also linked in the as-built report. So you got to remember, really important that you do get this put in to the right place, and it will fill. So to me, that's it's pretty straightforward filling out these reports, especially given that we've got the report guide here, a very quick reference. It's great having it right here. You don't have to go back to the manual. This is also in the manual, by the way. So if you want to see it, here's our manual, and it is in the control home. You'll find it in here, guidelines for completing. And so here's this table again in here. So you'll find, and lots more stuff to read in here. So I think we're coming to the end of this. And so we're just now going to. So who does the AHJ have to follow? The drawings or the compliance report. So these are the constructions. Yeah, and down here, based on information provided by the builder and drawings prepared by Amazing Design, dated this date. So make sure you get the drawings in there, but it also says information based on the builder. Now, if the HJs are not going to turn us into building inspectors, or where we have to go out and do field reviews, then the inspectors need something to inspect from. And so they're realizing that to meet code, energy efficiency code, what is listed here in the pre-construction report for assemblies and heating systems is how the house has to be built. And I see drawings that are not modified. We have conversations with the builder. Oh yeah, let's put 2 inches exterior on, or let's put, instead of R19 bat, we'll put R22 bat in the walls. We'll put a different kind of windows. The heating systems change, things like that. And that's not noted in the drawings that are put in for permit. So ideally, the drawings should be updated, but oftentimes the builders don't do that, and we have a variety of builders, from the incredibly efficient, huge tract builders, development builders, where everything works like a clock mechanism, right through to the very early spec house, build one house, hope to make some money kind of builders. And those kind of builders are overwhelmed anyways, and so those drawings aren't going to change. So really, the AHJ is going to go on our reports. So these reports need to be accurate for the inspectors to be able to inspect. They should be based on these drawings, and I would like to see a revision date in here. A lot of drawings have the same date for years and years, but they'll have different revisions, and so they should have a revision date on them. And so it should be, you know, the dated drawing and then dash REV, whatever date the revision is, or revision 01, 02, 03. The more information you have here, the better it is, because you really want to refer to the documents from where you took the information. So you want to remember to do that. Does the statement of where the info come from need to change? Yeah, it could be modified a little bit, and that'll happen in iterations. So it'll probably be a little bit more exact. I'm a bit uncomfortable with the get out of jail free card, information provided by the builder and drawings prepared by. Really, information that comes from the builder should be confirmed by the builder. There should be documentation to confirm it. You know, hi, according to our conversation the other day, you wanted this kind of a heat pump modeled and this type of a hot water system modeled. You wanted the envelope changed to this and this. This is what we did. Please confirm. And then you have a confirmation in your records. So this could be information and drawings prepared by. So that would be a little bit better. Appendix as a companion to section B. Section B here, and so having an appendix, it's been brought up, and I think it's probably a good idea that we develop something in the future for that. It's, this will be like it is for a little while longer. This is being recorded in December of 2020. So we're not going to be doing anything over Christmas, that's for sure. And we'll see where the code goes in January and February, see if there's any updates. But really, to have a fuller, to be able to expand on this a little bit more fully would be really nice, to have the space to do that. So that could be another page, and so maybe a 4-page report where this is expanded on a little bit better rather than a 3-page report. What info does an AHJ want or need? So some AHJs wanted the full house report from HOT 2000, the one I was pulling up and pulling data out of. It's not a problem. It's, if for clients, we have some clients that want that as well, and I do some modeling for CMHC. They wanted the full house reports. So what I do say is how you label your constructions, how I label my constructions becomes a little bit more important because it needs to be a little bit more descriptive. So attic wall or exterior wall, attic knee wall, things like that. Attic knee wall would explain why it doesn't have drywall on why it has drywall on both sides, or garage wall has drywall on both sides rather than wall 1, wall 2, wall 3. So you may want to think about that so they can follow a little bit closer. Generally, when they want those full-on reports, they're looking at the accuracy. So you are being looked at when they ask that, and the modeling is being looked at. I get a little bit nervous because there aren't very many people working for AHJs that are qualified to do auditing on our files who are trained to do what we do, but there are some. And they will look at it and make sure that what we put in makes sense. The bottom line for all of this, for the AHJs looking, is they're liable for the construction of the house. And when they work with professionals, architects, engineers, geotechs, things like that, the liability falls on those professionals' shoulders. It's not clear where the liability falls yet for when they're using EAs. Yes, we hold liability insurance, but really that liability insurance, I'm not quite sure it's caught up with the reality that we're doing code compliant work for that. So we're being looked at as a new area, a new trade or profession or whatever area we fall into. And we're being assessed. You know, do we deserve, what level do we deserve? Do we have a code of ethics? Is there an organization that QAs us or is the oversight? And when the AHJ doesn't feel that there is any oversight, then they are going to provide the oversight because it is their toes that are in the fire, so they feel. And there's cases to be made for that, for sure. So just know that some AHJs are more nervous than other AHJs. Some AHJs have more or less skill sets as far as energy modeling on board, as far as building science understanding on board. A lot of AHJs, as we know, we start adding exterior insulation, and they start getting really nervous about water entrapment, water vapor condensation entrapment within the envelope itself for mold and rot conditions and things like that. So they are a partner. Bottom line, they are a partner, along with the builder and the designer and us and the tradespeople. We're all partners in building this particular building to the highest standard that we can. And we're all asking for information and trusting each other that each other can do what we need to do, and that we have the skill set to do what we do. And because this is still early days for code compliance, for energy advisors, we're being looked at a little bit closer. So yeah, just remember that as we go along. That's it for me. I wish you all the best out there. I hope that this webinar served to clarify many things for you. Thanks much. See you later.
If you do have any questions following from this presentation, we encourage you to write the BC Building Standards Branch email of codequestions@government.bc.ca and to review the energystepcode.ca website. Thank you very much for joining us and watching us this recording of the BC Energy Compliance Report Generator Training for Energy Advisors and Service Organizations. We appreciate the time you've invested in watching this video.